Hello, and welcome to The Sleepy Scientist. If you've found your way here, you're probably looking for a gentle way to wind down. And what better way to do that than with a slow, calming dive into the chemistry of nearly everything. From the quiet elegance of atoms bonding in the dark to the barely audible chaos of molecules colliding, tonight's journey is all about the invisible forces behind everything you touch, taste, and tiptoe around. I'll do my best to keep things soothing and steady, but fair warning, the universe is pretty fascinating. I hope this video isn't so interesting that it keeps you wide-eyed and alert, but if it does, well, at least you'll drift off a little wiser than before. Before we begin our gentle descent into the molecular world, if you enjoy this kind of calm, curious content, I'd be truly grateful if you could tap the like button and consider subscribing. It helps this little corner of the internet stay cozy and curious, and if you feel like sharing, let me know where in the world you're listening from, and what time it is for you right now. I always love seeing how far the sleepy science travels. Now settle in, let your breath slow, let the day's thoughts float gently away. Tonight we're going to explore why things react, bond, explode, or sometimes just sit there doing absolutely nothing at all. Oh, and while we'll be talking a bit about chemistry in the body and brain later on, nothing in this video is meant as medical advice. Just friendly, fact-checked bedtime science. Imagine holding something in your hand. Anything, really. A spoon, a feather, a half-eaten cookie. Now imagine cutting that object in half, then in half again, and again, and again, until you couldn't possibly cut it any further. You'd eventually end up with something so small, so fundamentally tiny, that it stops being that object and becomes something else entirely, an atom. Atoms are the building blocks of all matter. Everything around you, your pillow, your toenails, your favourite tea mug, the screen you're staring at, is made of atoms. In fact, you're made of atoms. You're a walking, talking, occasionally yawning cloud of organised particles. And while atoms themselves are incredibly small, the science behind them is anything but boring. Let's start at the very beginning. An atom is made up of three main types of particles: protons, neutrons, and electrons. If atoms were solar systems, the protons and neutrons would be huddled together in the centre like a sun forming the nucleus. Electrons would be the speedy little planets, zipping around the nucleus in what we call orbitals, though it's not exactly like planets orbiting a star. In reality, electrons behave more like clouds of possibility than precise dots. They exist in fuzzy regions where they are likely to be, but we can never say exactly where they are at any given moment. They're elusive little things, like introverts at a crowded party, always just out of reach. The nucleus, on the other hand, is dense and central. Protons have a positive charge, neutrons have no charge, and together they form the heavy heart of the atom. Protons determine what element an atom is. For example, every atom with just one proton is hydrogen, and every atom with 6 protons is carbon. Add or subtract a proton, and you're no longer dealing with the same element. It's like a strict name tag policy at a cosmic conference. No switching roles allowed. Neutrons, while electrically neutral, play a crucial role in keeping the peace. Without them, the positively charged protons would repel each other with considerable force. Neutrons help glue the nucleus together, offering a kind of diplomatic calm in an otherwise tense subatomic space, and they do it all without taking sides. Now the electrons, these are the sprightly nimble ones. They have a negative charge and exist in various energy levels or shells around the nucleus. The farther from the nucleus they are, the more energy they hold. Electrons are like the social butterflies of the atom world, or perhaps social lightning bugs, constantly darting, shifting, and occasionally leaping to higher energy states when given the right push, like from heat or light. But here's where things get even more intriguing. Atoms are mostly empty space. If a nucleus were the size of a pea, the nearest electron would be floating somewhere several hundred feet away. That means everything solid you touch, including your own body, is made up of particles suspended in vast voids of nothingness. Matter feels solid not because it's packed tight with stuff, but because of the invisible forces between these particles. It's like standing in a room full of invisible walls. You can't see them, but you're very aware of where they begin and end. Each atom is incredibly small, about 1/10 billionth of a metre in diameter. To put that into perspective, a single grain of sand contains more atoms than there are stars in the observable universe. And yet, each of those atoms plays by the same basic rules, following the same quiet choreography of attraction, repulsion, bonding, and sometimes rebellion. When atoms come together, they form molecules, which can then form just about anything: gases, liquids, solids, stars, and you. But even alone, a single atom can tell a fascinating story. Take helium, for instance. Just 2 protons, 2 neutrons, and 2 electrons. It's light, unreactive, and a bit aloof. It doesn't like to bond with others, preferring to float solo, quite literally. Then there's oxygen, which is more of a social type, always looking to pair up, ready to form bonds, and essential to just about every breath you take. You could almost imagine atoms at a party. Helium off in the corner, sipping punch quietly, while oxygen and hydrogen are on the dance floor forming water and causing a bit of a splash. Of course, not all atoms are stable. Some are radioactive, meaning their nuclei are a little too ambitious for their own good. They decay over time, breaking apart and releasing energy in the process. It's a dramatic end for something so tiny, and yet it powers everything from smoke detectors to the core of the Earth. Even instability has its role in this vast atomic drama. What's remarkable is how predictable all of this is. Thanks to centuries of science and experimentation, we can now understand how atoms behave with impressive accuracy. We can map out their configurations, predict how they'll interact, and even manipulate them to build entirely new materials, medicines, and technologies. It's the ultimate blueprint, one that doesn't require instructions, just a deep understanding of the rules and a good deal of patience. Atoms also make up the periodic table, that beautifully ordered grid of elements you may remember from school. Each square is a different kind of atom, with its own unique personality and role in the universe. Some are gregarious and bond easily, others are stubborn and solitary. Some are heavy and slow, others light and reactive. The table isn't just a scientific reference. It's a kind of character map for the fundamental players in the universe. Even though we've come to understand so much about atoms, they remain full of wonder. They obey the strange rules of quantum mechanics, where particles can exist in multiple states at once, and where just observing something can change its behaviour. It's science at its most poetic, and its most perplexing. Atoms don't think or feel, of course. They don't know that we're talking about them. But if they did, perhaps they'd be amused to know that these tiny invisible bits of existence are the stars of the show. Quietly, invisibly, they shape everything, including the thoughts we have, the dreams we dream, and the breaths we're taking right now. So here we are, nestled in a world built from countless tiny somethings, most of which are empty space, dancing according to laws they've followed for billions of years. And yet, somehow, in all that stillness and emptiness, life emerges, consciousness emerges, you emerge, and it all starts with the atom, the smallest something that makes up everything. Let's take a moment to appreciate electrons, the tiny, zippy, wildly unpredictable particles that are somehow responsible for nearly every chemical reaction you've ever seen, smelled, or accidentally set off in a school science lab. Electrons may be lightweights, nearly 2,000 times less massive than protons. But what they lack in size, they more than make up for in energy and attitude. Electrons don't behave the way we might expect. In fact, the deeper you dive into their world, the stranger things get. If protons and neutrons are the dependable, steady folks holding down the fort in the nucleus, electrons are more like excitable artists on roller skates, constantly moving, difficult to pin down, and likely to start something dramatic if the conditions are right. Let's begin with the basics. Electrons carry a negative electric charge, and they're drawn toward the positively charged protons in the nucleus, not unlike a moth to a glowing light bulb. This attraction keeps them from drifting off into the void, but it doesn't mean they settle down quietly. Electrons move constantly, and their behaviour is best described not by a neat orbit like planets around the Sun, but by something far more elusive, the probability cloud. In classical physics, you could describe where an object is and where it's going, but electrons don't play by classical rules. They belong to the quantum realm, where location and momentum are slippery concepts. Instead of drawing a dotted line to mark an electron's path, scientists use a fuzzy cloud of probabilities to show where an electron is likely to be found at any given moment. The denser the cloud, the more likely the electron is hovering in that spot. It's a bit like looking for a cat in a large house. You don't know exactly where it is, but based on past experience you know it's probably curled up near a warm window, under the bed, or halfway inside a cardboard box. These clouds, or orbitals, come in different shapes and sizes. Some are spherical, some are dumbbell-shaped, and others look like something only a sleep-deprived artist could dream up. Orbitals group together in layers called shells, which are arranged around the nucleus. Each shell can hold a certain number of electrons. The first holds up to 2, the second up to 8, the third up to 18, and so on. Electrons prefer to occupy the lowest available energy levels first. This is known as the Aufbau principle, and they only move to higher shells when there's no more room down below, or when they've absorbed extra energy. Now here's where it gets interesting, or, depending on your taste in metaphors, electrifying. An atom's reactivity depends largely on its outermost electrons, also known as valence electrons. These electrons live in the atom's highest energy shell, and are the ones most likely to interact with other atoms. If an atom's outer shell is full, it tends to be stable and unreactive, a bit like someone who's already comfortably wrapped in a blanket with a cup of tea. But if that outer shell is incomplete, the atom starts looking for ways to gain, lose, or share electrons, which is where all the bonding drama begins. Consider the noble gases, like helium or neon. Their outer shells are full, and as a result they barely interact with other atoms. They're the chemistry equivalent of contented introverts, happy to be left alone. Then you have elements like sodium, which has just one lonely electron in its outer shell. That electron is itching to leave, to find a new home and reach a more stable configuration. On the flip side, chlorine is just one electron short of a full outer shell, and would love nothing more than to adopt an extra one. When sodium meets chlorine, they're a match made in chemical heaven. Sodium donates its extra electron to chlorine, and together they form sodium chloride, ordinary table salt, and just like that, dinner is saved. This drive for stability, often referred to as the octet rule, helps explain why certain atoms form specific types of bonds. Atoms will do all sorts of things, share electrons, steal them, give them away, just to fill up the outer shell. Sometimes it's a fair exchange, like in covalent bonds where atoms share electrons equally. Other times it's more of a mugging, like in ionic bonds where one atom gives up an electron entirely and another snatches it up. Energy also plays a big role in electron behaviour. When an atom absorbs energy from heat, light, or even electricity, its electrons can get excited, literally. An excited electron absorbs energy and jumps to a higher shell, farther from the nucleus. It doesn't stay there long though. Electrons like stability, and before you know it, the excited electron will fall back to its lower energy level, releasing that energy as light. This is the basis for everything from neon signs to the glowing gas clouds found in deep space. It's also the principle behind fireworks. Heat excites the electrons in different metal atoms, and when they drop back down, they release bursts of light in brilliant colours. Electrons are also the reason metals are shiny and conduct electricity. In metals, electrons can move freely between atoms, a sort of communal cloud shared by the entire structure. These free-moving electrons reflect light, giving metals their characteristic luster, and allow electric current to flow smoothly through them. It's like a subatomic conga line that powers your toaster. In the realm of chemistry, electrons are the ultimate matchmakers, peacekeepers, and occasional troublemakers. Their behaviour determines whether atoms will bond, what type of bond will form, how strong that bond will be, and how easily it can be broken. Reactions start when electrons are tempted away from their usual positions. A little push here, a little energy there, and suddenly a new compound is born. But electrons don't just influence chemical reactions, they also shape the physical and chemical properties of matter. The number and arrangement of electrons affect how substances look, feel, and behave. Whether something is a gas, a solid, or a liquid depends in part on how tightly electrons hold atoms together. Whether something is acidic or basic, conductive or insulating, shiny or dull, electrons are pulling the strings. Even the colours we see are a result of electrons. Pigments absorb certain wavelengths of light and reflect others, depending on how their electrons respond to energy. A ripe strawberry appears red because its electrons absorb most other colours and bounce back red wavelengths. The blue in the sky, the green of leaves, the shimmer of oil on water. It's all electrons absorbing, emitting, and interacting with light in their own peculiar ways. What's even more mind-bending is that we still don't fully understand them. Electrons are governed by quantum mechanics, a field so strange and counterintuitive that even the scientists who work in it sometimes describe it as surreal. Electrons can act like particles or waves, or sometimes both at once. They can be in multiple places until observed. They can tunnel through barriers they shouldn't be able to cross. They're slippery, strange, and utterly essential to the chemistry of life. In the end, electrons may be tiny, but they are the restless hearts of atoms, always in motion, always influencing the world around them. From the bonds that hold molecules together to the sparks that fly when you touch a doorknob, electrons are responsible. They are the quiet agitators, the energetic instigators, the invisible artists behind the patterns of reality. And even though we can't see them directly, we feel their effects every moment, in our bodies, in our breath, in the very act of thinking. Each thought is an electric signal carried by electrons, fluttering through neurons like tiny flashes of curiosity. Small? Yes. Shifty? Definitely. But without them, the universe would be a very dull and very dark place. Place indeed. If atoms had personalities, chemical bonds would be their relationship statuses. Some are clingy, some are generous, and some just want to hang out in a metallic free-for-all. But no matter how different they seem, all bonds exist for the same fundamental reason: stability. Atoms are constantly trying to reach a lower energy state, and bonding helps them get there. In other words, atoms form relationships not out of sentiment, but out of a deeply logical quest for balance. Let's start with the most classic of atomic pairings, the covalent bond. Picture two kids sharing a snack, not in the one gets everything and the other gets crumbs sort of way, but a fair, mutual, synchronized sharing. That's what covalent bonding is. Two atoms each bring an electron to the table, and together they share the pair like a tiny electron fondue. It's a peaceful arrangement. Everyone contributes. Everyone benefits. Covalent bonds are especially common among non-metals. Oxygen and hydrogen, for example, come together to form water by sharing electrons. Each hydrogen brings one, oxygen brings two, and together they complete their outer shells like puzzle pieces sliding into place. This bond isn't just functional, it's foundational. Water's molecular structure gives it its unique properties, from surface tension to its ability to dissolve almost anything. All thanks to atoms politely sharing their electron snacks. But not all atoms are so courteous. Sometimes one atom wants electrons so badly that it just takes them outright. This is where ionic bonds come in, the aggressive shoppers of the chemical world. Instead of sharing, one atom donates an electron, and the other greedily accepts it. In the process, both become charged. The atom that loses an electron becomes positively charged, while the one that gains it becomes negatively charged. These oppositely charged ions are then pulled together by electrostatic attraction, like two magnets drawn together. Sodium and chlorine are a textbook example of this bold, unequal exchange. Sodium has one lonely electron it's eager to give away. Chlorine is one electron short of a full shell and wants desperately to complete its set. Sodium hands over its electron like a hot potato, and chlorine clutches it triumphantly. They transform into sodium ions and chloride ions, stick together and become sodium chloride, or as it's known in kitchens around the world, table salt. In ionic bonding, there's no sharing or negotiation. It's a full handover, a clean transfer of ownership. The resulting ions are strongly attracted to each other, forming solid crystalline structures, those neat little geometric stacks that make salt crystals sparkle under the light. Then there's metallic bonding, a different kind of social dynamic altogether. Picture a neighbourhood potluck where everyone brings a dish, leaves it on a communal table, and no one remembers which plate belonged to whom. That's metallic bonding in a nutshell. In metals, atoms don't just bond with their immediate neighbours. Instead, their outer electrons are delocalized. They wander freely through the entire structure like tiny partygoers, mingling from atom to atom. This electron sea is what gives metals their characteristic properties. Because electrons can move so freely, metals conduct electricity easily. Those mobile electrons form a smooth, unbroken path for current. The same fluidity is responsible for the shiny, reflective surfaces of metals and their ability to be shaped without breaking. When you hammer a piece of copper or bend a wire, the atoms can shift while still remaining bonded thanks to the sea of electrons cushioning the structure. Now you might wonder, why do atoms go to all this trouble? Why form bonds at all? The short answer is energy. Every atom wants to be in the lowest possible energy state, and bonding is one of the best ways to get there. When atoms bond, they release energy, moving from a higher energy solo existence to a lower energy bonded state. It's the atomic equivalent of collapsing onto the couch after a long day. Finally, everything is calm and stable. The outermost electrons, those valence electrons, are the matchmakers in this whole scenario. Atoms are most reactive when their outer shells are incomplete. A hydrogen atom, with just one electron, wants to find a buddy to complete its shell. A fluorine atom, missing just one, is eager to pair up. These needs drive atoms to seek out others, forming connections that satisfy both. Sometimes these bonds are incredibly strong. Diamonds, for instance, are a lattice of carbon atoms held together by a rigid network of covalent bonds. Each carbon atom forms 4 covalent bonds in a tetrahedral structure, creating one of the hardest materials known. On the other hand, some bonds are quite weak, like the attractions between water molecules. These are called hydrogen bonds, not quite full-fledged chemical bonds, but still strong enough to hold things together in surprising ways. They're what give water its high boiling point, and allow insects to walk across the surface without sinking. Bond strength depends on many factors, including the type of atoms involved, their electronegativity, and how tightly they can hold on to shared or transferred electrons. Electronegativity, by the way, is a measure of how strongly an atom pulls on electrons in a bond. Fluorine, for example, is famously greedy. It has the highest electronegativity of all elements, and will pull shared electrons closer to itself in any covalent bond. On the opposite end, atoms like cesium are more relaxed, almost laissez-faire when it comes to electron custody. When bonds form, energy is usually released, a process called an exothermic reaction. When bonds break, energy is absorbed, an endothermic reaction. That's why lighting a fire takes effort. You need to input energy to break the bonds in the wood, but once they break and new bonds form in the combustion products, energy floods out in the form of heat and light. Reactions often involve a complex mix of breaking and forming bonds. A single reaction might snap old connections and forge new ones in a flash, all driven by the shifting desires of electrons. Sometimes the process is slow and steady, like rust forming on metal. Other times, it's rapid and explosive, as in the case of fireworks, where bonds are broken and formed in milliseconds, releasing heat, light, and sound. The world around you is held together by countless invisible bonds, each one a result of atoms seeking stability. Your own body is a vast ongoing symphony of chemical bonding, proteins folding into precise shapes via covalent and hydrogen bonds, DNA strands held together by base pair attractions, enzymes forming brief relationships with molecules to speed up vital reactions. Even your thoughts are made possible by the firing of neurons, which depends on ionic exchanges across cell membranes. Bonds aren't just about structure, they're about function, life, memory, and change. At the end of the day, bonding is chemistry's way of creating order from chaos. Whether atoms share evenly, steal outright, or contribute to a communal pool, the goal is the same: lower energy, greater stability, and the potential to build something new. A gas becomes a liquid becomes a solid, a spark becomes a flame, all because of the endless ways atoms link, rearrange, and hold on to one another. It's strangely poetic, really. The same forces that glue salt crystals together are also at work in stars, cells, and snowflakes. Whether it's a molecule of sugar or a bar of gold, everything we see, taste, and touch owes its existence to the tiny partnerships between atoms, a silent, ceaseless dance of give and take, of holding hands and letting go. Energy is the heartbeat of every chemical reaction. It's the invisible currency traded between atoms as they form or break bonds, reshape themselves, or transform into something entirely new. But even the most reactive chemicals usually need a bit of a push to get going. This little push is what chemists call activation energy, the minimum amount of energy required to start a reaction. Without it, even the most promising combination of ingredients would just sit there in awkward silence, like two people at a dinner party waiting for someone else to make the first move. Take a box of matches. Inside, you've got everything you need for fire, chemicals that are eager to react, oxygen from the air, and a wooden stick just waiting to be transformed into smoke and ash. And yet nothing happens until you strike the match. That friction provides the activation energy needed to kick-start the reaction. Heat is introduced, molecules begin to vibrate more vigorously, bonds start to stretch and break, and new ones quickly form. In the blink of an eye, combustion begins. Without that initial spark, though, the match would remain perfectly still, no matter how flammable its ingredients might be. That's because molecules are lazy in their natural state. Or, to put it more politely, they prefer to stay in their current arrangements unless something comes along to jostle them out of their comfort zones. Activation energy is that gentle, or sometimes not so gentle, nudge. To picture activation energy, imagine pushing a boulder over a hill. The boulder represents your set of reactant molecules, sitting comfortably at the base of the hill. To get to the other side, the product side, the boulder must be pushed uphill first. That uphill effort is the activation energy. Once the boulder reaches the top, it rolls down the other side with ease. Likewise, once a reaction passes that energy barrier, it tends to move forward without much additional effort. Some reactions need very little energy to begin, others require quite a lot. That's why certain chemicals can sit safely on your shelf for years without reacting, while others burst into flame at the slightest provocation. It's not just about what the molecules can do, it's about how much energy it takes to convince them to do it. Now let's talk about what happens after a reaction gets started. Once those initial bonds begin to shift and shuffle, energy is either absorbed or released. This brings us to two important types of reactions: endothermic and exothermic. Endothermic reactions absorb energy from their surroundings. It's like feeding the reaction a steady diet of heat in order to keep it going. The classic example is photosynthesis, the process by which plants convert carbon dioxide and water into glucose and oxygen using sunlight. Without that steady stream of solar energy, the whole process grinds to a halt. In fact, the reason plants grow toward the light is because their chemistry literally depends on it. Another example of an endothermic process is the instant cold packs used in first aid kits. These contain water and a separate pouch of ammonium nitrate. When the two are mixed, the reaction absorbs heat from the surroundings, rapidly lowering the temperature. The cold you feel isn't being added by the reaction, it's being taken from your skin as heat is absorbed. On the flip side, we have exothermic reactions, the warm, generous types that release energy, usually in the form of heat, light, or both. Combustion is perhaps the most dramatic example. Light a candle, and you're watching hydrocarbons in the wax reacting with oxygen to produce carbon dioxide, water vapour, and a satisfying amount of heat and flame. Fireworks, explosions, and even the metabolism of food inside your body are all driven by exothermic reactions. In fact, your cells are little combustion chambers, just much more polite. When you eat a banana, the sugars are broken down in a controlled step-by-step series of exothermic reactions. These reactions release energy that your body uses to power everything from blinking to dreaming. You don't burst into flames every time you snack, thankfully, because the energy is released in manageable doses, regulated by enzymes and other molecular traffic directors. Some reactions can go either way depending on the circumstances. Water evaporating, for instance, is endothermic. It absorbs heat to escape into the air as vapour, but when that vapour condenses back into liquid, it releases heat in an exothermic process. These reversible reactions create a sort of energetic dance, shifting depending on the environment. Interestingly, many reactions that seem explosive or violent actually involve relatively modest changes in chemical bonds. It's the speed and quantity of the changes that create drama. A pile of dry leaves slowly decomposing over months is a chemical reaction. These same leaves, set ablaze, transform in seconds. Both processes ultimately involve rearranging carbon, hydrogen and oxygen atoms, but one takes a leisurely path and the other charges ahead in a fiery burst of exothermic enthusiasm. Catalysts can also influence activation energy. These are substances that speed up a reaction by lowering the energy barrier, making it easier for the reactants to reach that magical tipping point. Catalysts don't get used up in the process. They just facilitate the meeting of molecular minds. Think of them as matchmakers in the world of chemistry, quietly encouraging bonds behind the scenes. Enzymes, which are biological catalysts, play this role in nearly every process inside living organisms. Without enzymes, your body's chemistry would be so sluggish that you wouldn't survive. Reactions that should take milliseconds might instead take years. Your digestive system, for example, would stare blankly at a slice of bread without the help of enzymes to break down the starches and proteins into usable energy. Catalysts don't provide the energy themselves, they simply make the path smoother. The idea of activation energy also helps explain why some substances are unstable. If a molecule is perched precariously at the top of a high-energy state, it may only need a nudge to collapse into something else. This is the case with unstable explosives or reactive chemicals. They've already paid most of their activation energy, entry fee, and now they're just waiting for someone to open the door. Sometimes that someone is heat, light, friction, or even just time. Safety measures often revolve around controlling this energy threshold. That's why volatile chemicals are stored in cool, dark places. The less external energy available, the harder it is for a reaction to begin. It's also why many medicines are kept in refrigerators, and why aerosol cans carry warnings about heat. All of it comes down to energy management on a molecular level. In a way, chemical reactions are just nature's way of reorganizing atoms to reach a more comfortable energy level. It's not unlike adjusting your pillows before sleep, rearranging until everything feels just right. Some atoms prefer their new arrangements to be warmer and cozier, others require a bit of a warm-up first, and sometimes it takes a spark to get anything moving at all. Whether it's the warmth of a hand warmer, the cool sting of a cold pack, or the soft glow of a candle, you're witnessing the play of energy, moving, transforming, and occasionally exploding. It's never random. There's always a reason why something happens, and almost always that reason involves just the right amount of energy arriving at just the right moment. It's easy to take these transformations for granted. We flick a lighter, stir ingredients in a pan, or watch sunlight pour through a window, all without thinking about the energetic ballet happening at the atomic level. But behind every flame, every breeze, every breath lies a reaction, sparked, balanced, and quietly driven by the rules of energy. And often, all it takes to begin is a little push. Acids and bases are the mood makers of the chemical world. When they enter a reaction, things tend to get lively. They can make metal fizz, change the colour of a solution, or even turn cabbage juice into a chemistry experiment. And while they're often thought of as opposites, they're really just two sides of the same reactive coin, both defined by how they interact with water and how they deal with two particularly important ions, hydrogen ions written as H+, and hydroxide ions OH-. To understand acids and bases, let's start with water. Water, though it may seem perfectly neutral and peaceful, is in a constant quiet tug-of-war. At any given moment, a tiny number of water molecules split apart into H+ and OH- ions. Then, just as quickly, they recombine back into water. It's a delicate balance, like a calm conversation in a room full of whispering molecules. Now, an acid is any substance that increases the concentration of hydrogen ions when added to water. You can think of it as a generous donor, always handing out H+ ions to the solution. On the flip side, a base is a substance that either removes those hydrogen ions or adds hydroxide ions. In essence, acids push the balance toward more H+, while bases tilt it toward more OH-. This balance is measured by something called the pH scale, which ranges from 0 to 14. A pH of 7 is neutral. That's pure water, right in the middle. Anything below 7 is acidic, and anything above 7 is basic or alkaline. The lower the number, the more acidic the solution. The higher the number, the more basic. It's a logarithmic scale, which means each whole number represents a 10-fold difference. So, a solution with a pH of 4 is 10 times more acidic than one with a pH of 5. Lemon juice, with a pH around 2, is quite acidic. Vinegar, which is acetic acid, sits around pH 3. On the other side of the scale, baking soda is mildly basic, usually around pH 9, while bleach can reach a highly alkaline pH of 12 or even 13. At those extremes, both acids and bases can become corrosive, reactive, and occasionally very dramatic. Chemically speaking, what makes an acid so reactive is its tendency to give up hydrogen ions. These positively charged particles are small, but mighty. Once released into solution, they can interact with other molecules in all sorts of ways, altering chemical structures, speeding up reactions, or even damaging tissues, which is why strong acids can burn. Bases, meanwhile, either mop up those free hydrogen ions or contribute hydroxide ions that neutralize them. This interaction between acids and bases, the tug-of-war over H+ ions, is at the heart of countless chemical reactions. Acids and bases show up everywhere. In your stomach, hydrochloric acid helps digest food by breaking down proteins and killing unwanted microbes. Your pancreas responds by releasing bicarbonate, a mild base, to neutralize that acid once it leaves the stomach. It's a careful balancing act, acidic enough to digest, but not so acidic that it burns a hole through your intestines. Chemistry, thankfully, is often better at moderation than humans are. In cooking, acids add brightness and flavour. Think of lemon juice on a salad or vinegar in a marinade. They help denature proteins, making tough meat more tender, or turning milk into cheese. Bases are less common in the kitchen, but they have their uses too. Baking soda, for instance, releases carbon dioxide gas when mixed with an acid, causing dough to rise. Without that reaction, bread would be dense and uninspiring. One of the more satisfying demonstrations of acid-base chemistry is neutralization. When an acid and a base meet in just the right amounts, they react to form water and a salt. Not necessarily table salt, but any ionic compound made from the acid's negative ion and the base's positive ion. This neutralization can happen subtly or with great fanfare, depending on the strength of the reactants. Take vinegar and baking soda. Vinegar, being acidic, donates hydrogen ions. Baking soda or sodium bicarbonate acts as a base and accepts those ions. The result is a bubbly release of carbon dioxide gas, along with water and a harmless salt. It's harmless fun in a science fair volcano, but it's also an elegant chemical handshake, a peaceful resolution between opposites. At the more extreme end, mixing strong acids with strong bases can produce heat and even dangerous reactions. Bleach, for example, is highly basic. If you were to pour vinegar into bleach, the acid-base reaction would release toxic chlorine gas. Not something to try at home. In chemistry, opposites may attract, but they don't always get along peacefully. The way acids and bases affect chemical reactions goes beyond simple bubbling or colour changes. They can change the structure of molecules, disrupt or enhance chemical pathways, and act as catalysts or inhibitors. In living organisms, this sensitivity to pH is crucial. Enzymes, those helpful proteins that speed up reactions in your body, are highly dependent on pH. If the environment becomes too acidic or too basic, the enzyme might lose its shape and stop working. This is called denaturation, and it's one reason your body maintains such tight control over blood pH, keeping it around 7.4. Just a small shift in that balance can lead to serious health problems. Some organisms have evolved to thrive in extreme pH conditions. Acidophils, for example, are microbes that live in acidic environments like volcanic springs or acid mine drainage. On the other end of the spectrum, alkalophils survive in very basic conditions such as soda lakes. Their cellular machinery is adapted to conditions that would destroy most other life forms. It's a reminder that chemistry isn't just happening in pristine lab flasks. It's out there in the wild, bubbling away at the edge of what life can tolerate. pH also plays a big role in the environment. Acid rain, caused by sulfur and nitrogen compounds released into the atmosphere, can lower the pH of lakes and soils, harming plants and aquatic life. Similarly, changes in ocean pH due to increased carbon dioxide levels, a process known as ocean acidification, affect the ability of marine creatures to build shells and maintain their internal chemistry. These shifts might seem small, but in systems finely tuned by millions of years of evolution, even slight changes can cascade into big effects. In industry, acid-base chemistry powers everything from wastewater treatment to battery technology. Lead-acid car batteries, for instance, use sulfuric acid to generate electricity through a series of controlled redox reactions. In textiles, acids are used to fix dyes to fabric. In cleaning products, bases help dissolve grease and grime. It's not magic. It's just hydrogen and hydroxide ions doing their usual dance. Indicators are another charming part of the acid-base toolkit. These are substances that change colour depending on pH. Litmus paper turns red in acid and blue in base. Phenolphthalein, a favourite in chemistry classrooms, is colourless in acidic environments but turns bright pink in basic ones. Red cabbage juice, believe it or not, works as a natural pH indicator too, shifting through a rainbow of colours depending on the solution's acidity. These colourful transformations make acid-base reactions some of the most visually satisfying in chemistry. They're not just educational, they're downright theatrical. But behind the colourful fizz and foam is a deep and elegant system that governs countless processes in our bodies, our environment, and our technology. At its heart, acid-base chemistry is all about balance, the push and pull between giving and taking, between too much and not enough. Whether it's vinegar neutralising a wasp sting, antacid calming a sour stomach, or bleach scrubbing a stubborn stain, the story is the same. Ions interacting, electrons shifting, and molecules rearranging into something new. Acids and bases may seem like opposites, but they're really partners in a kind of molecular negotiation. One offers, the other accepts, and in just the right proportions they find peace, a stable, neutral place where the fizzing stops and the chemistry settles down, at least until someone adds lemon juice to the salad again. Temperature and pressure may seem like things you adjust on a thermostat or an air pump, but in the world of chemistry, they're master manipulators. They coax molecules to dance, collide, and react, sometimes slowly, sometimes explosively, all by altering the way particles move. You could say they're the ultimate party planners for the molecular world, setting the scene for reactions to begin. To understand how this works, let's visit one of the most important ideas in chemistry, the kinetic molecular theory. At its heart, this theory says that all matter is made of particles in constant motion. Even in something that seems completely still, a chunk of ice, a block of wood, or your own fingertips, atoms and molecules are vibrating, jiggling, and bouncing around. The hotter the substance, the faster they move. The cooler it is, the slower the jiggle. Imagine a room full of people walking aimlessly. If they're all strolling calmly, bumping into one another might be rare. But if you turn up the energy, maybe play loud music or offer everyone a double espresso, the movement intensifies. People start moving faster and the chance of collisions goes way up. The same is true for molecules. Heat is energy, and when you add it to a system, particles gain kinetic energy. They move faster, collide more often, and with greater force. Chemical reactions happen when molecules collide in just the right way, with enough energy to break old bonds and form new ones. Heating a substance increases the frequency and energy of these collisions, making it more likely that a reaction will occur. That's why cookies bake faster in a hot oven, why food spoils more quickly in warm weather, and why your metabolism speeds up when you have a fever. Heat gets things moving, quite literally. There's a threshold to cross though. Not every collision causes a reaction. Molecules need to collide with sufficient energy, and at the right orientation. It's not unlike tossing puzzle pieces at each other. Only when they hit just right will they snap together. The added energy from heat helps more of those puzzle pieces land correctly, increasing the chances of a successful reaction. Now let's bring pressure into the picture. Pressure is all about how tightly particles are squeezed together. In gases especially, where molecules are far apart and flying around freely, changing the pressure can have a huge impact. Increase the pressure and you're forcing molecules into a smaller space, cramming them closer together. With less room to roam, collisions become more frequent, and that increases the odds of a reaction taking place. Think of it like this. If you're at a concert in a wide open field, you might have plenty of space to spread out and avoid bumping into people. But if that same crowd is packed into a small club, you're going to be brushing shoulders constantly. In chemistry, those shoulder bumps are potential reaction points, and pressure makes them happen more often. Temperature and pressure don't just make reactions happen faster, they can also change what kinds of reactions occur and what products are favoured. Some reactions only occur at high temperatures or under extreme pressure. Others reverse direction if you adjust the conditions. This is particularly important in industrial chemistry, where fine-tuning heat and pressure can maximise yield and efficiency. A famous example is the Haber process, which produces ammonia from nitrogen and hydrogen gases. On their own, nitrogen and hydrogen don't have much interest in each other. They're like distant acquaintances at a dinner party, polite, but not particularly eager to mingle. However, under high temperature and very high pressure, with the help of a catalyst, they finally hit it off and form ammonia. That reaction is now responsible for much of the world's fertilizer, and by extension much of our food supply. Temperature also affects the rate constant of a reaction, which is a measure of how quickly it proceeds. This relationship is described by the Arrhenius equation, a mathematical expression that shows how even small changes in temperature can lead to large changes in reaction speed. The higher the temperature, the greater the proportion of molecules that have enough energy to overcome the activation energy barrier. In a way, heat helps more molecules reach that all-important tipping point. But temperature doesn't just speed things up, it also changes the nature of substances themselves. Solids melt into liquids, liquids evaporate into gases, and gases condense back into liquids, all depending on how much energy is floating around. Ice melts because heat gives water molecules enough energy to break free from their rigid structure. Steam forms when those same molecules gain even more energy and escape into the air. These phase changes are physical, not chemical. The molecules themselves stay the same, but they demonstrate how powerful heat can be at disrupting structure. Some reactions actually slow down when heated, though they're in the minority. In a few cases, high temperatures destabilize the products or shift the balance of equilibrium. That's why, in sensitive biological systems, there's often a sweet spot. Too cold and things slow to a crawl, too hot and everything starts to unravel. Pressure also has its quirks. While it mainly affects gases, it can change the rate of reactions involving solids and liquids too, especially when the volume of the system changes during the reaction. If a reaction produces fewer gas molecules than it started with, increasing the pressure can drive it forward. If it produces more, raising the pressure can slow it down. It's all about shifting the balance in favour of less crowding. This tug-of-war between heat and pressure plays out in countless everyday experiences. Cooking is a perfect example. Pressure cookers trap steam and raise the internal pressure, which in turn raises the boiling point of water. That lets food cook faster at higher temperatures without drying out. Stews become tender, beans soften, and tough cuts of meat transform into something delicious, all because of a little applied physics and chemistry. Another example is deep-sea chemistry. At extreme ocean depths, the pressure is immense, hundreds of times higher than at sea level. This changes the behaviour of gases, affects solubility, and even alters reaction pathways. Microorganisms living near hydrothermal vents thrive in conditions that would flatten most life forms, using the heat and pressure to drive unique biochemical reactions. Life, it seems, is extraordinarily adaptable when it comes to thermodynamic constraints. In the lab, chemists manipulate temperature and pressure with precision. Reactions that take days at room temperature might finish in minutes when heated. Pressurized reaction vessels, called autoclaves, allow for reactions that wouldn't normally occur in open air. Even in pharmaceutical manufacturing, controlling temperature ensures that delicate molecules form correctly, with the right structure and purity. But managing these factors is a delicate art. Too much heat and sensitive compounds can decompose. Too much pressure and containment becomes a serious engineering problem. Sometimes the goal isn't speed at all, but control. Allowing reactions to proceed slowly and predictably, reducing the chance of unwanted side products or explosions. What's remarkable is how universal these principles are. Whether you're baking bread, studying volcanoes, designing rocket fuel, or fermenting yogurt, the same basic rules apply. Heat adds motion, pressure adds proximity, and together they influence the course of chemistry in subtle and spectacular ways. Even the weather is governed by these rules. Clouds form when warm, moist air cools and condenses. Lightning is the result of charge separation in turbulent, heated clouds. Thunder, believe it or not, is the sound of the air being rapidly heated and expanding faster than the speed of sound. A crack of thunder is chemistry, physics, and atmosphere colliding, quite literally, in dramatic style. So much of what we observe in the world is shaped by invisible forces acting on tiny particles. Molecules don't decide to react. They're guided by energy, movement, and proximity. Heat gives them the speed. Pressure gives them the squeeze. Together they unlock the possibilities of transformation, one collision at a time. From the stillness of ice to the shimmer of steam, from the crushing pressure beneath the ocean to the calm hum of a kettle, the dance of particles continues, always moving, always colliding, always responding to the push and pull of their environment. And at the heart of it all, a simple truth. Nothing reacts without a little motivation. Temperature and pressure just happen to be excellent motivators. In the neat world of textbooks, chemical reactions often look like one-way streets. You start with reactants, mix them up, And voila! Products appear, the reaction is done, and everyone moves on. But in reality, chemistry is rarely so final. Reactions often go both ways. Molecules don't just combine and call it a day. They separate, rejoin, and sometimes flip back and forth endlessly. This is the world of reversible reactions, where the finish line is more of a roundabout than a dead end. A reversible reaction is exactly what it sounds like, a chemical process that can proceed in both directions. Reactants become products, but those products can also break down to become reactants again. It's a chemical tug of war, where both sides are pulling, and neither fully wins. Instead of one side collapsing, the system settles into a state of balance, a kind of truce where both directions happen at the same time, in just the right proportions. This balance is called equilibrium. It doesn't mean that nothing is happening. On the contrary, at equilibrium, the reaction is still occurring. Molecules are still forming and breaking apart, but they're doing so at equal rates. It's like watching people walk up and down an escalator at the same speed. The number of people at the top and bottom stays the same, but the movement never stops. The concept of chemical equilibrium is central to understanding how many natural and industrial processes work. It explains why some reactions never seem to finish, why others appear to stall halfway, and why changing the environment can tip the balance one way or another. It's not that the reaction is indecisive, it's that chemistry, at its core, loves to find a balance between competing forces. Let's imagine a simple reversible reaction. Two colourless gases, hydrogen and iodine, react to form a deep purple gas called hydrogen iodide. At first, as the hydrogen and iodine are mixed, purple gas starts forming. But as more and more hydrogen iodide accumulates, some of it begins to break back down into hydrogen and iodine. Eventually, the rate at which hydrogen and iodine combine is equal to the rate at which hydrogen iodide splits apart. The result? A mixture of all three gases, locked in a dynamic dance where nothing really changes, and yet everything is constantly moving. This equilibrium is a delicate thing. It depends on temperature, pressure, concentration, and even the presence of catalysts. And here's where a helpful bit of chemical wisdom comes in, courtesy of the 19th century French chemist Henri Le Chatelier. He observed that when you disturb a system at equilibrium, the system responds in a way that tries to counteract the disturbance. This idea is known as Le Chatelier's principle, and it's surprisingly intuitive. Imagine a room with a thermostat set to a cosy temperature. If someone opens a window and cold air rushes in, the heating system kicks on to bring the temperature back to where it was. Chemistry behaves in much the same way. If you add more reactants to a system at equilibrium, the reaction shifts to use them up, producing more products. If you remove products, the system scrambles to replace them. If you crank up the heat, the system responds in a way that absorbs that heat, often by favouring the endothermic direction of the reaction. Let's take a real-world example, the equilibrium between nitrogen dioxide and dinitrogen tetroxide. Nitrogen dioxide is a brown gas, while dinitrogen tetroxide is colourless. The reaction goes both ways, and at equilibrium, the mixture has a faint brown tint. But if you cool the gas, the brown fades. More dinitrogen tetroxide forms, absorbing heat. Warm it up again, and the brown colour deepens as more nitrogen dioxide appears. The system is constantly adjusting, trying to undo whatever change was introduced. Pressure works the same way, especially in reactions involving gases. If you increase the pressure by squeezing the gas into a smaller volume, the system shifts toward the side of the reaction with fewer gas molecules, trying to reduce the pressure. If the reaction produces more gas molecules, the pressure rises and the equilibrium shifts to counter that. It's all a matter of balance, of molecules trying to spread out or huddle together depending on their crowded surroundings. Even the concentration of individual substances can sway the equilibrium. Add more of one chemical, and the reaction tilts to consume it. Take some away, and the reaction pivots to replace it. It's chemistry's version of adjusting to change. graceful, reactive, and quietly persistent. Equilibrium is especially important in biological systems. Our bodies rely on countless reversible reactions that must remain finely tuned. Take the oxygen-carrying protein hemoglobin, for example. In the lungs, where oxygen concentration is high, the equilibrium favours binding. Oxygen sticks to hemoglobin. In the tissues, where oxygen levels are lower, the equilibrium shifts and oxygen is released. It's an elegant automatic adjustment that happens with every breath and every heartbeat. Another vital example is the carbonic acid equilibrium in our blood. Carbon dioxide dissolves in water to form carbonic acid, which then breaks down into bicarbonate and hydrogen ions. This reversible reaction helps maintain blood pH within a narrow range. If carbon dioxide levels rise, more acid forms, lowering pH. If they fall, the reaction reverses. Your body uses this system, along with your lungs and kidneys, to stay in chemical harmony. In industrial chemistry, mastering equilibrium can mean the difference between a successful product and a costly failure. The synthesis of ammonia in the Haber process, for instance, involves a reversible reaction between nitrogen and hydrogen. By manipulating temperature, pressure, and concentration, chemists can shift the equilibrium to favour ammonia formation. It's a constant balancing act between chemistry and efficiency. Equilibrium doesn't mean equal amounts of reactants and products. It just means the forward and reverse reactions happen at the same rate. In some cases, the mixture may contain mostly products. In others, it may be mostly reactants. It all depends on the energy dynamics of the reaction, which direction is more stable, and how much energy is required to go back and forth. There's something poetic about equilibrium. It reminds us that nature doesn't like extremes. It prefers moderation, compromise, and feedback loops. The world isn't full of reactions that go one way and stop. Instead, it's full of reversibility, of systems that adjust, respond, and settle into a state where everything seems calm on the surface, even though there's motion underneath. This constant push and pull is why nothing is ever truly finished reacting. Even in a bottle of vinegar on your kitchen shelf, tiny shifts are still occurring. In the atmosphere, gases are constantly exchanging, reacting, and redistributing. Even in solid rocks over long timescales, atoms rearrange, minerals transform, and equilibrium slowly drifts from one state to another. Equilibrium is a dynamic pause, a point where change doesn't stop but balances itself out. It's the moment when the tug-of-war rope stops moving, not because the pulling has stopped, but because both sides are pulling equally hard. It's not peace through stillness, it's peace through motion. Understanding this principle opens up a deeper view of the world. You start to notice balance everywhere. In chemical reactions, in ecosystems, in social dynamics, systems respond to pressure, resist disruption, and find new steady states. Chemistry just happens to be very good at showing us how it works. So the next time you hear about something being in balance, or you notice steam condensing back into water, or you simply take a deep breath, remember this: equilibrium isn't the end of a reaction. It's the beginning of something more subtle, a quiet, continuous, invisible negotiation, where molecules agree to keep going, but only if everything stays fair. Explosions are chemistry's most dramatic outbursts, the big, showy spectacles that demand attention. They're fast, fiery, loud, and often a little terrifying. But behind the booms and bangs lies a surprisingly elegant principle: rapid energy release caused by chemical reactions. An explosion is simply chemistry done at high speed, often in confined spaces, with little regard for subtlety. To understand what makes something explode, we need to first understand what an explosion actually is. At its core, an explosion is a sudden expansion of matter, accompanied by a rapid release of energy, typically in the form of heat, light, gas, and shock waves. That release can be caused by a chemical reaction, a physical process like decompression, or even a nuclear event. But the common thread is speed. Reactions that happen in milliseconds, releasing enormous amounts of energy all at once. Most chemical explosions involve combustion, a type of reaction in which a substance reacts quickly with oxygen to produce heat and light. Combustion isn't always explosive. A candle flame, for example, is a gentle, controlled burn. But if you change the conditions, add more fuel, more oxygen, or contain it tightly, the same chemistry can become explosive. Take a balloon filled with hydrogen. Alone, it's harmless. But add a spark, and the hydrogen rapidly reacts with oxygen in the air to form water vapour. The reaction releases a large amount of energy, and because it happens so quickly, the surrounding air expands almost instantly, creating a shock wave and a very satisfying bang. The key to most explosions is rapid oxidation. Oxidation is the process of losing electrons, and in the case of combustion, the fuel molecules lose electrons to oxygen. This transfer releases energy as chemical bonds are broken and new, more stable bonds form. In a slow burn, that energy is released gradually. In an explosion, it's unleashed all at once, like a tightly wound spring suddenly let go. Fireworks are a perfect example of how controlled explosions can be beautiful. Each firework is a tiny chemistry lab packed with oxidizers, fuels, and colour-producing compounds. When ignited, the oxidizer helps the fuel burn rapidly, producing hot gases that propel the firework into the sky. As it bursts, different metal salts create the vivid colours: strontium for red, barium for green, copper for blue, and sodium for yellow. It's not just an art form, it's chemistry doing choreography. Then there's TNT, trinitrotoluene, one of the most famous explosives. TNT is an example of a compound that contains both fuel and oxidizer in the same molecule. When detonated, it rearranges its atoms incredibly quickly, producing gases like nitrogen and carbon monoxide, along with an enormous release of heat. Because the gases expand so rapidly, and because the energy release happens faster than the surrounding materials can absorb it, the result is an explosion. What makes TNT particularly interesting is that it's actually quite stable under normal conditions. You can drop it or handle it without setting it off. It needs a detonator, a smaller, more sensitive explosive, to provide the precise energy required to overcome its activation barrier. Once started, though, the reaction propagates rapidly through the material, turning solid explosive into a storm of hot gas and pressure in an instant. Explosions can be either deflagrations or detonations, depending on how the reaction spreads. In a deflagration, the reaction moves through the material at subsonic speeds, like in gunpowder. In a detonation, the reaction front moves faster than the speed of sound, creating a shock wave that does most of the damage. The distinction matters. It's the difference between a firecracker and a high-powered explosive. But explosions aren't always violent by intention. Sometimes they're the result of accidents. Unexpected chemical reactions that happen when the right ingredients come together under the wrong conditions. And believe it or not, one of the most common places for accidental explosions is your own kitchen. Let's start with flour. On its own, flour seems harmless. It's soft, dusty, and makes great cookies. But suspend that flour in air, add a spark, and you've got a potential dust explosion. That's because the tiny particles have a large surface area relative to their volume, making them highly reactive when mixed with oxygen. If the dust is dense enough and confined, a single flame can ignite the whole cloud in a flash. This is why flour mills have explosion-proof equipment, and why it's wise not to let your kitchen resemble one during baking adventures. The same goes for aerosol cans. Those little pressurized cylinders contain flammable propellants. If heated, the internal pressure builds until the can bursts. If that happens near an ignition source, the results can be explosive. Even something as innocent as oil in a pan can become dangerous. Overheated oil can catch fire, and adding water to an oil fire is a recipe for disaster. The water rapidly turns to steam, ejecting the burning oil in all directions and creating a fireball that would impress even a professional stunt coordinator. Then there's the classic reaction between baking soda and vinegar. Not quite explosive, but definitely enthusiastic. When the acid, vinegar, reacts with the base, baking soda, it produces carbon dioxide gas, which quickly expands and causes bubbling, fizzing, and sometimes a mess on your countertop. While not dangerous, it's a reminder that even simple kitchen ingredients are full of reactive potential. In other settings, explosive reactions are harnessed for practical use. Car airbags, for instance, deploy using a controlled explosion. Inside the airbag module is a chemical like sodium azide. When triggered, it rapidly decomposes, producing nitrogen gas that inflates the airbag in less than 1/10 of a second. That controlled blast can save lives, all thanks to chemistry moving at top speed. In mining and construction, explosives like dynamite and ANFO, ammonium nitrate and fuel oil, are used to move massive amounts of rock and earth. These materials are carefully designed to be stable during handling, but release huge amounts of energy when detonated properly. Their power lies not just in their composition, but in the way the reaction propagates through the material, a carefully calculated chain reaction of molecular rearrangement. Explosions even play a role in the natural world. Volcanoes are perhaps Earth's most dramatic chemists, combining heat, pressure, and reactive gases to produce eruptions. Deep underground, molten rock mixes with water and gases like carbon dioxide and sulfur dioxide. When pressure builds high enough, the mixture erupts, releasing heat, ash, and gas in explosive fashion. It's a reminder that the Earth itself is always reacting, simmering, and sometimes bursting at the seams. On a much smaller scale, even cells can experience miniature chemical explosions. The bombardier beetle, for instance, defends itself by squirting a boiling hot chemical spray from its abdomen. It stores two reactive compounds, hydrogen peroxide and hydroquinone, in separate chambers. When threatened, it mixes them together in a reaction chamber, where enzymes catalyze a violent reaction that releases heat and pressure. The resulting burst of gas propels the mixture outward, scalding predators and demonstrating that even nature knows how to mix an impressive chemical cocktail. Explosions are not inherently bad, they're just fast reactions doing what reactions do, breaking bonds, forming new ones, and releasing energy. The challenge is in managing them. Too slow, and the reaction fizzles. Too fast, and it destroys everything in its path. Chemists, engineers, and cooks alike have learned to walk that fine line, harnessing explosive chemistry to power engines, launch spacecraft, save lives, and entertain crowds. It's easy to think of explosions as outliers, loud, extreme events at the far edge of chemistry. But in truth, they're just reactions accelerated. The same principles apply whether you're lighting a candle or igniting rocket fuel. It's about energy, molecules, and the rate at which change unfolds. So the next time you watch fireworks burst across the sky or hear popcorn explode in a microwave, you're witnessing the same process in action, atoms rearranging themselves in a rush of heat, sound, and expansion. It's chemistry unleashed, not chaotic, just fast, and sometimes gloriously loud. Carbon is the undisputed diva of the periodic table. It's not the flashiest element, not the heaviest or the rarest. But when it comes to versatility, charisma, and sheer range, carbon steals the spotlight. It's the element with a flair for drama, structure, and transformation, the molecular shapeshifter that builds everything from butterflies to bananas, from your DNA to the graphite in your pencil. If chemistry had a red carpet, carbon would be the one arriving fashionably late in a limousine made of itself. What makes carbon so special is its ability to bond, and not just once or twice, but up to 4 times at once. This might not sound like much, but in the microscopic world of atoms, 4 is a magic number. It allows carbon to form incredibly stable, flexible, and complex structures. Chains, rings, branches, double bonds, triple bonds. Carbon does it all. And it does it with a kind of elegance that has made it the foundation for all known life. At the heart of organic chemistry, the branch of chemistry that studies carbon-based compounds, is this remarkable ability of carbon atoms to connect with each other and with other elements in endless combinations. That self-bonding talent, known as catenation, is the root of carbon's versatility. No other element can rival it. Silicon, which sits just beneath carbon on the periodic table, tries its best, but it's the karaoke version of carbon at best. Carbon is the original, and life wouldn't be here without it. Organic molecules are basically carbon-based frameworks dressed up with functional groups, small clusters of atoms that define how the molecule behaves. Like costumes in a play, these groups give each molecule a specific role. Add an OH group and you get an alcohol. Swap in a -COOH and it's a carboxylic acid. Throw on a -NH2 and it becomes an amine. It's all carbon underneath, but with different accessories carbon can play almost any part. Let's talk structure, because carbon doesn't just form molecules, it builds architecture. Straight chains are the simplest form, where carbon atoms link up in a line, but things get fancier quickly. Those chains can branch, bend, or loop into rings. Cyclohexane, for example, is a 6-carbon ring that looks like a miniature hexagonal playground. Aromatic rings, like benzene, bring even more sophistication, with a resonance structure that allows electrons to float around in a shared cloud, a feature that makes them unusually stable and chemically interesting. Some organic molecules are huge, like proteins, which are long chains of amino acids folded into precise shapes, or DNA, which twists into a double helix stretching out to billions of atoms. Others are tiny, like methane, just 1 carbon bonded to 4 hydrogens. But no matter the size, the rules are the same. Carbon in the middle, bonds going out in all directions, holding everything together like a molecular socialite, with impeccable networking skills. Carbon's 4 bonding arms also allow it to form double and triple bonds. In a double bond, 2 pairs of electrons are shared between atoms, creating a stronger and shorter bond than a single one. Triple bonds with 3 pairs of shared electrons are even stronger and shorter. These types of bonds change the reactivity and geometry of molecules, and they're part of what gives organic chemistry its depth and complexity. Then there are isomers, molecules with the same chemical formula but different structures. Carbon loves isomers. It can take the same handful of atoms and arrange them into totally different shapes, leading to compounds with wildly different properties. Butane and isobutane, for example, both have the formula C4H10, but their structures differ, and so do their boiling points, melting points, and how they behave in chemical reactions. It's a bit like rearranging the furniture in a room. The piece is the same, but the result feels completely different. Stereochemistry adds another layer of intrigue. Some molecules have the same atoms and the same bonds, but are mirror images of each other, like left and right hands. These are called enantiomers, and they can have dramatically different effects in biology. One enantiomer of a drug might relieve pain, while its mirror twin could be ineffective or even harmful. The way living organisms interact with molecules is often incredibly specific, and carbon's ability to arrange itself in 3-dimensional space with such precision is part of what makes life so exquisitely tuned. Organic chemistry is sometimes jokingly called the chemistry of life and carbon-based confusion, and it's not hard to see why. The molecules are many, the names are long, and the rules are full of exceptions. But within that complexity lies a beautiful order, a system built on a small atom with big ambitions. Life as we know it is basically one long carbon experiment. Proteins, lipids, carbohydrates, nucleic acids, the 4 great classes of biological macromolecules, are all carbon-based. Enzymes, which catalyze the reactions in your body, are proteins folded into elaborate shapes, each one tailored to a specific task. Membranes that hold cells together are built from lipid molecules, forming flexible, self-sealing barriers. Carbohydrates like glucose serve as quick energy, while starches and cellulose provide structure and storage. And DNA, that spiral staircase of life, carries your genetic code in a molecule made almost entirely of carbon, hydrogen, oxygen, nitrogen, and phosphorus. All of these functions, storing energy, replicating instructions, building structure, rely on carbon's ability to form stable yet dynamic bonds. It's strong enough to hold things together, but not so strong that molecules become rigid or inert. Life needs that balance. It needs a scaffold that can support complexity, but still allow for change, motion, and mutation. Even the origin of life likely hinged on carbon chemistry. Scientists studying the early Earth or simulating conditions on other planets often look at how simple carbon compounds might have formed spontaneously, laying the groundwork for more complex structures. In laboratory conditions, mixtures of gases and electrical sparks have yielded amino acids and other building blocks of life. These experiments suggest that with the right ingredients and a little time, carbon is quite capable of building something extraordinary. Organic chemistry also stretches far beyond biology. In material science, carbon forms everything from synthetic polymers to cutting-edge nanomaterials. Plastics, for better or worse, are organic compounds, long chains of repeating carbon units. Carbon nanotubes and graphene are pushing the boundaries of strength and conductivity, promising new technologies from flexible electronics to space elevators. Even fuels like gasoline and natural gas are hydrocarbons, carbon chains with hydrogen sidekicks, packed with stored energy waiting to be released. Carbon's versatility is also reflected in its various pure forms. As graphite, it's soft and slippery, perfect for pencils and lubricants. As diamond, it's hard and brilliant, a lattice of carbon atoms locked in an incredibly strong three-dimensional network. The difference between these two substances is not what atoms they're made of, but how those atoms are arranged. Same element, entirely different personalities. And of course, carbon is the central figure in climate chemistry. Carbon dioxide, a simple molecule with one carbon and two oxygens, is a vital greenhouse gas, essential in small amounts, but problematic in excess. Its ability to trap heat has made it a focal point in discussions about global warming, sustainability, and our collective impact on the planet. Carbon is not just the stuff of life, it's the stuff of consequence. Despite its fame, carbon isn't flashy in appearance. It's usually black or colourless, and it doesn't sparkle unless you squeeze it into diamond form. But in the world of atoms, carbon is the quiet genius. It builds the molecules of life, the materials of modernity, and the cycles of nature. It bends, bonds, loops, and links in ways that other elements can only dream of. If chemistry were a theatre production, carbon would be the writer, the director, the lead actor, and the set designer, always on stage, always involved, but rarely drawing attention to itself unless things go spectacularly right or horribly wrong. It's the reason you're made of molecules instead of moon rocks, the reason your cells function, your food digests, and your brain thinks. And all of that, every heartbeat and breath and blinking eye, comes down to one element with 4 bonding arms, a love of structure, and an endless capacity for forming connections. Carbon isn't just the diva of the periodic table, it's the storyteller of life. Redox sounds like the name of a futuristic cleaning product or a sci-fi robot, but in reality it's one of the most important chemical processes in the universe. Short for reduction oxidation, redox reactions are all about the exchange of electrons, those tiny energetic particles that make atoms tick. Wherever something is burning, rusting, charging, or digesting, you can bet redox chemistry is quietly running the show behind the scenes. At its core, a redox reaction is like a well-coordinated game of electron musical chairs. One substance loses electrons and another gains them. That's it. The trick is that these two processes, oxidation and reduction, always happen together. You can't have one without the other, because an electron doesn't just vanish into thin air. If one atom gives one up, another has to take it. It's a constant chemical relay of give and take. Let's start with definitions. Oxidation is the loss of electrons, while reduction is the gain of electrons. It might sound backward, especially since the word reduction seems like it should involve losing something. But in chemistry, gaining negatively charged electrons makes the overall charge of a species more negative, or reduced. A helpful way to remember this is the acronym OILRIG. Oxidation is loss, reduction is gain. Electrons are the energetic currency of atoms, and during a redox reaction, they're passed around like hot potatoes. Some atoms are natural electron hoarders. Oxygen, for instance, is very good at pulling electrons toward itself, which is why it features so prominently in oxidation reactions. Others are more generous, readily parting with electrons to achieve a more stable configuration. Let's look at a simple but iconic redox reaction, the rusting of iron. When iron is exposed to water and oxygen, it slowly transforms into iron oxide. The reddish-brown, flaky stuff that forms on old garden tools and forgotten bicycles. Here's what's happening. The iron atoms lose electrons, which makes them oxidized. Those free electrons are then picked up by oxygen in the presence of water, reducing the oxygen atoms. The result is iron oxide, or rust, which is chemically stable but structurally weak. Left unchecked, rust will keep eating away at the iron, which is why metal bridges, ships and cars need constant protection. The rust doesn't just sit on the surface like a stain. It's a sign that electrons have changed hands, and the material beneath is slowly being transformed. Rust might be annoying, but it's a gentle, creeping example of redox in action. Other redox reactions are more energetic. Combustion, for example, is an oxidation reaction on fast forward. When you burn wood, gasoline, or a marshmallow, the carbon and hydrogen in the fuel lose electrons to oxygen, releasing energy in the form of heat and light. The rapid transfer of electrons causes bonds to break and form in a cascade of energy, giving us flames and warmth. It's chaotic and beautiful and entirely the work of redox chemistry. But redox isn't just about things falling apart, it's also how your body generates energy. Inside your cells, a process called cellular respiration breaks down glucose, a sugar molecule rich in energy. During this process, electrons are stripped from glucose and pass through a series of proteins in the mitochondria, creating a controlled flow of electrons that ultimately powers the production of ATP, the cell's energy currency. Oxygen is the final electron acceptor in this chain, which is why you need to breathe. Without oxygen to catch those electrons, the whole system grinds to a halt. This carefully orchestrated flow of electrons is eerily similar to what happens in a battery. In fact, batteries are essentially portable redox reactions. Inside a typical battery, you have two different materials, one that easily gives up electrons, the anode, and one that eagerly accepts them, the cathode. When the battery is connected in a circuit, electrons flow from the anode to the cathode through the wire, powering your flashlight, phone, or singing birthday card. Inside the battery, ions move through an electrolyte to balance the charge, completing the circuit. Take a simple alkaline battery. The anode is usually made of zinc, which gets oxidized. It loses electrons. The cathode is made of manganese dioxide, which gets reduced as it gains those electrons. The whole setup is arranged so that this electron flow happens in a controlled, steady manner, generating electricity without flames or sparks. It's silent, reliable redox at work. Rechargeable batteries like lithium-ion ones use reversible redox reactions. When you charge them, electrons are pushed backward through the system, restoring the original chemical states. It's like rewinding the movie so you can watch it again later. These reactions are carefully balanced, and managing them well is part of what makes battery design both brilliant and tricky. Redox reactions also show up in photosynthesis, the process plants use to turn sunlight into sugar. In a green leaf, light energy splits water molecules, pulling electrons away from hydrogen and passing them through an electron transport chain. The electrons eventually help convert carbon dioxide into glucose, storing energy in chemical bonds. It's the opposite of cellular respiration. Instead of burning sugar to release energy, the plant is using energy to build sugar. In both cases, though, electrons are on the move, always changing hands in carefully choreographed sequences. In the lab, redox reactions are used for things like electroplating, where a metal object is coated with a thin layer of another metal. A current is passed through a solution, causing metal ions to gain electrons and deposit onto the object. This can protect the surface from corrosion, or just make it shiny. Your silverware, jewellery and chrome car parts might all owe their finish to redox reactions. Redox chemistry even helps monitor health. Blood glucose meters use tiny redox reactions to detect sugar levels. Breathalyzer devices detect alcohol through oxidation, and many water treatment systems use redox reactions to remove harmful contaminants, either by oxidizing them into less dangerous forms or by reducing them into substances that can be filtered out. One of the fascinating things about redox is how it ties into electron affinity, how strongly an atom wants to gain electrons, and ionization energy, how much effort it takes to remove an electron. These properties determine who wins and who loses in the chemical game of musical chairs. Fluorine, for example, is the ultimate electron hog. It will pull electrons from almost anything, which makes it incredibly reactive. On the other hand, alkali metals like sodium practically fling their electrons at the first taker, making them excellent reducing agents. In redox chemistry, these roles are formalized. The substance that loses electrons is called the reducing agent, because it reduces the other substance by giving up electrons. The one that gains electrons is the oxidizing agent, because it oxidizes the other by stealing electrons. It's a kind of odd generosity. By giving something up, you cause a reduction, and by taking, you cause oxidation. It's a deeply relational chemistry where nothing happens in isolation. What makes redox reactions so compelling is that they're everywhere. They power life, industry, nature, and even some of the gadgets you carry in your pocket. They can be slow, like rust inching across an old fence, or fast, like a spark that lights up a gas stove. They can be beneficial, like the energy from food, or dangerous, like corrosion weakening a bridge. But they all come down to electrons finding new homes. Every redox reaction is a story of change, of atoms adjusting to a new balance, of electrons finding better neighbourhoods, of systems shifting in pursuit of lower energy. It's chemistry at its most dynamic and interconnected. And like a good exchange, it only works when both sides play their part. Whether in a leaf, a lung, or a lithium battery, electrons are always moving. And with them, the world turns quietly onward. In the grand theatre of chemistry, most attention goes to the big players, the atoms reacting, the bonds breaking, the energy being flung around like confetti. But tucked quietly behind the curtain are the unsung heroes that make it all happen faster, smoother, and with far less drama. These are the catalysts, the quiet helpers of the molecular world. They don't take centre stage, they don't change themselves, but without them, many reactions would move so slowly that you'd still be waiting for your cookies to bake next Thursday. At its core, a catalyst is a substance that speeds up a chemical reaction without being consumed in the process. It's a sort of molecular matchmaker, helping reactants find each other and encouraging them to get on with the bonding already. Once the reaction is finished, the catalyst steps aside, unchanged and ready to do it all again. It's the ultimate facilitator, efficient, discreet, and quietly indispensable. Let's say two molecules want to react, but the path to get there is blocked by a high-energy barrier, the dreaded activation energy. Maybe they don't collide quite right. Maybe the bonds are too stable. Maybe they're just being stubborn. Enter the catalyst. It provides an alternate route, a shortcut with a lower energy barrier. The result? The reaction happens more quickly, using less energy, and without needing to raise the temperature or pressure. It's like using a secret side street to skip a traffic jam. Same destination, but with a lot less honking. Catalysts come in many forms. In industry, there are metals like platinum and nickel that catalyze everything from hydrogenation to fuel processing. In cars, catalytic converters help transform toxic gases into less harmful ones before they escape out the exhaust pipe. But the most elegant and astonishing catalysts of all are found inside your own body: enzymes. Enzymes are biological catalysts made of proteins, and they're astonishingly good at their jobs. They can speed up reactions by factors of millions or even trillions, turning slow, lumbering chemical steps into lightning-fast transformations. Without enzymes, your body would fall apart, literally. Digestion, cell repair, energy production, immune responses, all of it relies on enzymes working around the clock to keep you alive and functioning. Each enzyme is highly specific. It usually works with just one particular molecule, a substrate, and catalyzes just one type of reaction. The enzyme structure includes an active site, a specially shaped pocket that fits the substrate like a glove. When the substrate enters, the enzyme holds it in just the right position to break or form bonds efficiently. Sometimes the enzyme contorts the molecule slightly, destabilizing its bonds and making them easier to rearrange. Other times it brings two molecules together, nudging them into perfect alignment for a reaction. Once the reaction is complete, the product molecules drift away, and the enzyme resets, ready for another round. It's like a molecular assembly line where the workers never tire, never take breaks, and never get paid. Just quietly keep everything running. A classic example is the enzyme catalase, found in nearly all living cells. Its job is to break down hydrogen peroxide, a byproduct of metabolism that can be harmful if it accumulates, into harmless water and oxygen. One molecule of catalase can convert millions of hydrogen peroxide molecules each second. It's chemistry on fast forward, and you can even watch it happen. If you add hydrogen peroxide to fresh potato or liver, you'll see bubbling as the oxygen is released. That's catalase in action, protecting cells from oxidative stress. Another star enzyme is amylase, which starts breaking down starches in your saliva the moment you start chewing. That's why bread or crackers taste slightly sweet if you keep them in your mouth. The long chains of starch are being chopped into simpler sugars by enzymes right there on your tongue. Enzymes are sensitive to their environment. Changes in temperature, pH, or salt concentration can affect their shape and function. If the conditions stray too far from what the enzyme likes, it may denature, lose its shape, and stop working. This is why fevers can be dangerous and why the body works hard to maintain homeostasis. The chemistry of life is balanced on a knife's edge, and enzymes are at the very centre of it all. Outside of biology, catalysts play major roles in everything from energy to manufacturing. In the Haber-Bosch process, which produces ammonia from nitrogen and hydrogen, an iron catalyst makes the reaction practical at an industrial scale. Without it, we wouldn't be able to produce the massive quantities of fertilizer needed to feed billions of people. In fact, it's been said that half the nitrogen in your body, in your DNA, proteins and muscles, was fixed from the air by this process, made possible by a humble metal catalyst. Catalysts also help create plastics, pharmaceuticals, synthetic fuels, and countless other products. Zeolites, for instance, are microporous minerals used in refining petroleum. They act like sieves, sorting and rearranging hydrocarbons with incredible precision. Transition metals like palladium and rhodium are used in fine chemical synthesis, where even small improvements in speed or yield can mean big cost savings. In green chemistry, catalysts are essential for making processes more sustainable. By lowering energy requirements, reducing waste, and enabling reactions to happen under milder conditions, catalysts help make chemistry more efficient and less harmful to the environment. They're not just helpers, they're the quiet force behind a more responsible way of doing science. Some catalysts are even inspired by nature. Biomimetic catalysts are synthetic compounds designed to imitate the function of enzymes. They may not have the complexity of a living protein, but they can offer similar specificity and efficiency. It's a field that's expanding rapidly, blending biology, chemistry and engineering in ways that could transform medicine and materials science. Interestingly, not all catalysts speed things up forever. Some are designed to stop working at a certain point, self-deactivating or switchable, catalysts that can turn on or off in response to specific triggers. These can be used in drug delivery, where the catalyst activates only under the right conditions, or in smart materials that change their properties in response to heat, light, or acidity. In teaching chemistry, catalysts are sometimes overlooked, seen as supporting characters rather than leads. But once you start noticing them, you realise they're everywhere. They enable change without changing themselves. They make the impossible routine. They accelerate progress without stealing the spotlight. It's hard not to admire that kind of quiet confidence. In a world where most reactions require heat, pressure, or brute force, catalysts are the smooth operators, slipping in, nudging atoms into place, and gliding away before anyone notices. They're chemistry's backstage crew, setting the scene, arranging the props, and making sure the stars shine as brightly as possible. And perhaps that's why catalysts resonate so much. They remind us that influence doesn't always mean centre stage. That transformation can come from gentle nudges, subtle shifts, and behind-the-scenes brilliance. That sometimes the greatest power lies in enabling others to do what they were meant to do. Just a little faster, a little easier, and with far more grace. Water is, without a doubt, one of the strangest substances on Earth, and one of the most essential. It's everywhere. It covers most of the planet. It fills the air as vapour. It flows through your veins, and it makes up the bulk of every cell in your body. And yet, for something so familiar, water is quietly full of mystery. It bends the rules of chemistry, breaks expectations, and holds everything, including us, together with an elegance that's easy to overlook. At a glance, water seems simple. 2 hydrogen atoms and 1 oxygen atom, H2O. But this tiny V-shaped molecule is anything but ordinary. Its peculiarities are the result of its shape, its polarity, and the strange bonds it forms with its neighbours, all of which give rise to water's many remarkable behaviours. Let's start with polarity. Water is a polar molecule, meaning it has a slightly positive end and a slightly negative end. The oxygen atom is more electronegative than hydrogen, so it pulls the shared electrons in the bond a little closer to itself. This creates a partial negative charge on the oxygen side and a partial positive charge on the hydrogen side. The result is a molecular tug-of-war that gives water its uneven charge distribution, like a tiny magnet with a north and south pole. This polarity is at the heart of water's personality. It allows water molecules to attract one another through hydrogen bonding, which is a bit of a misleading name. Hydrogen bonds aren't true chemical bonds, they're more like strong attractions between molecules. But they're powerful enough to hold water molecules together in ways that defy expectation. Hydrogen bonding gives water its unusually high boiling point. Most molecules of similar size and mass are gases at room temperature. Think methane or ammonia. But water is a liquid, and not just a liquid with surface tension strong enough to let insects walk on it, cohesion high enough to pull itself up the inside of plant stems, and a heat capacity so large it can absorb vast amounts of energy with only a small rise in temperature. That's why coastal climates tend to be milder. Water absorbs and releases heat more slowly than air or land, acting like a thermal cushion. It's nature's heat manager, evening out temperature swings and keeping life within a tolerable range. Without this ability, our planet would be full of extremes, scorching by day, freezing by night, a challenge for even the hardiest life forms. Another strange trick. Water expands when it freezes. Most substances shrink as they solidify, but water does the opposite. That's because its hydrogen bonds lock the molecules into an open hexagonal structure, which takes up more space than the jumbled state of liquid water. This is why ice floats. It's less dense than the liquid it came from. The consequences of floating ice are enormous. If ice sank, lakes and oceans would freeze from the bottom up, trapping aquatic life and changing the entire planet's climate. Instead, ice forms an insulating layer on the surface, preserving liquid water below and allowing ecosystems to survive harsh winters. It's a quirk of molecular geometry that ends up preserving life. Water's role as the universal solvent is another of its superpowers. Its polar nature makes it incredibly good at dissolving other substances, especially ionic compounds and other polar molecules. When you drop salt into water, the positive and negative ions that make up the salt crystal are surrounded and separated by water molecules, effectively pulled apart into solution. Water doesn't just dissolve salt, though. It dissolves sugars, gases, minerals, acids, and bases. It's why nutrients can travel through your bloodstream, why plants can draw minerals up from the soil, and why cleaning with water actually works. If water weren't such a talented solvent, we'd have a much harder time transporting anything useful, or getting rid of anything toxic. That said, water isn't great at dissolving everything. Non-polar substances like oils and fats resist mixing with water. This gives rise to the old saying, like dissolves like, meaning polar substances dissolve in polar solvents and non-polar ones in non-polar solvents. It's the reason oil and vinegar separate in salad dressing, and why soap, which has both polar and non-polar parts, is so useful. One end of a soap molecule binds to grease, the other to water, forming tiny droplets called micelles that can be rinsed away. In the microscopic world, water's properties shape every corner of biology. Inside your cells, water is the medium in which thousands of chemical reactions take place. Enzymes, DNA, proteins, they all fold and function in a watery environment. Water molecules help stabilize structures, shuttle ions, and even participate directly in some reactions. In proteins, for instance, water influences how they fold into their specific shapes, and shape determines function. A misfolded protein can't do its job properly and may even cause disease. Water is both the stage and a character in the biochemical drama of life. Water also plays a starring role in photosynthesis, where plants use sunlight to split water molecules, extracting electrons to help build sugars. The oxygen released during this process, the very oxygen you're breathing right now, comes directly from the water in plants. Every breath you take is a quiet echo of water's generosity. On a planetary scale, water helps sculpt landscapes, weather systems, and even geology. It erodes mountains, carves canyons, and delivers sediment to river deltas. It moves heat across the globe through ocean currents and shapes weather patterns with its transitions between liquid, vapour, and ice. The water cycle is a continuous, planet-spanning flow of evaporation, condensation, precipitation, and collection. It links oceans, clouds, rivers, glaciers, soil, and living organisms in a seamless, never-ending loop. Chemically, water is stable, but not inert. It can act as both an acid and a base, donating or accepting protons depending on the situation. This makes it an important participant in pH balance, buffering, and countless acid-base reactions in living organisms. It's flexible, adaptable, and always involved. Despite its abundance, water is surprisingly selective in where it's found and how it's distributed. Of all the water on Earth, only a tiny fraction, less than 1%, is readily available freshwater. The rest is locked up in oceans, glaciers, or deep underground. Every drop we drink, cook with, or shower in is part of a much smaller pool than most people realise. In space, the search for water is central to the search for life. Wherever scientists find liquid water, they get excited. Jupiter's moon, Europa, Saturn's Enceladus, the dusty subsurface of Mars, all of them show signs of water, and therefore the tantalizing possibility of life. Water may not guarantee biology, but it seems to be a necessary ingredient. And this makes sense when you consider what water brings to the table. It's a solvent, a temperature regulator, a structural stabilizer, a transport medium, and a reactant. It doesn't just support life, it enables it. Life as we know it is water-based not by coincidence, but because water is simply that good at what it does. Even on a personal level, you're more water than anything else. By weight, adult humans are around 60% water. Infants are closer to 75%. Your blood is mostly water. Your brain is mostly water. Even your bones contain water. It cushions your joints, regulates your temperature, flushes out waste and delivers nutrients to your cells. And yet, for all its importance, water is often overlooked. It flows through our lives quietly, unnoticed until something runs dry or goes wrong. But once you start to pay attention, it becomes clear just how strange, clever and vital this little molecule really is. Water is a rule bender, a shapeshifter, a quiet alchemist that holds the secrets of chemistry in a single drop. It may be transparent, but it's never simple, and for a molecule made of just 3 atoms, it carries more than its fair share of wonder. Matter at first glance seems like such a simple thing. It's the stuff everything's made of. The chair you're sitting on, the air you're breathing, the tea cooling on the table beside you. But beneath its everyday appearances, matter is constantly in motion, shifting between forms, vibrating with energy, and occasionally pulling off some unexpected transformations. Understanding the states of matter and how they change is like peeking behind the curtain of physical reality. It's less about rigid categories and more about a graceful dance of particles responding to temperature, pressure and energy. Traditionally, matter is taught in 3 basic states: solid, liquid and gas. Add plasma, and you've got the full classic quartet. But even those are just the beginning. There are exotic states like Bose-Einstein, condensates and superfluids that come into play under extreme conditions. For now, though, let's gently wander through the familiar states and see what makes them tick. Start with solids, the quietest of the bunch. In a solid, particles are arranged in a fixed, orderly structure. They don't have the freedom to roam, but they're not completely still either. Each atom or molecule vibrates in place, jiggling ever so slightly. Solids hold their shape because the particles are tightly bound together, their movements limited by strong intermolecular forces, or, in the case of metals and crystals, rigid lattice frameworks. When you touch a cold metal spoon or step onto a tiled floor in the morning, you're feeling the stability of this tightly packed particle grid. Whether it's a rock, a block of ice, or a wooden table, solids tend to resist change, at least until enough energy is added to loosen things up. Introduce heat, and the particles start to vibrate faster. They gain energy, stretching the bonds that hold them in place. At a certain point, called the melting point, those vibrations become strong enough to break the rigid structure. The particles don't fly apart, but they do slip past each other, and the solid becomes a liquid. Liquids are the social middle ground of matter. The particles are still close together, but they can move, flow, and slide around one another. A liquid takes the shape of its container, but maintains a fixed volume. It doesn't expand to fill space like a gas does. Water in a cup is water in a bowl is water in your hands. It changes shape, not size. The beauty of liquids is in their adaptability. Their molecules are in constant motion, bumping into one another and rearranging themselves, but still held together by intermolecular forces. Surface tension, viscosity, and capillary action are all expressions of these relationships. How closely the particles stick, how easily they move past each other, how they cling to surfaces. Now add more heat. The particles move faster still. They start to overcome the attractions that kept them loosely bound as a liquid. Eventually they reach the boiling point, the temperature at which liquid molecules have enough energy to break free and become gas. Boiling isn't just bubbling at the surface, it's a full-on escape from the liquid state. Particles shoot into the air, spreading out to fill the available space, no longer tied down by structure or cohesion. Gases are the wild spirits of the particle world. They're fast, far apart, and mostly independent. They expand to fill whatever space they're given and take the shape of their container. The air in a balloon presses against the inside of the rubber because gas particles are constantly bouncing off the walls. Open a window, and those same particles drift out. dispersing into the broader atmosphere. Because gas particles are so free to move, gases are compressible. You can squeeze them into smaller spaces like in scuba tanks or bicycle tyres. That's not something you can do with solids or liquids which are already tightly packed. In gases, the distance between particles is much greater, so they can be squished closer together, up to a point, with the help of pressure. But there's still more to the story. If you keep adding energy, cranking up the temperature far beyond boiling, gas particles can gain so much energy that the electrons are stripped away from their atoms. What you're left with is a soup of charged particles, free electrons and positive ions, all bouncing around energetically. This is plasma, the fourth classical state of matter. Plasma might sound exotic, but it's actually the most common state of matter in the visible universe. Stars, including our sun, are giant balls of plasma. Neon signs, lightning bolts, and the auroras near the poles, all plasma in action. It behaves a bit like a gas, but its charged particles respond to electric and magnetic fields in ways that make it distinctly different. Plasma is matter at its most electrified and exuberant. Now let's go back the other way. Remove energy, and particles slow down. A gas cools into a liquid into a solid. These reverse phase changes are just as interesting as the ones we've already explored. Condensation, when gas becomes liquid, is how dew forms on grass and water beads on a cold drink. Freezing is when those same water molecules slow down and lock into place, forming solid ice. Sometimes matter can skip a step. Sublimation is when a solid turns directly into a gas without becoming a liquid first. Dry ice, frozen carbon dioxide, is a great example. Leave it at room temperature and it doesn't melt. It vaporizes straight into gas, creating that dramatic fog you see in spooky stage shows or science demos. On the flip side, deposition is when gas turns directly into a solid. That's what happens when frost forms on a window pane. Water vapour in the air crystallises without passing through the liquid stage. All of these transitions, melting, freezing, boiling, condensing, sublimating, depositing, are phase changes. They don't change the identity of the substance, just its form. Ice, liquid water, and steam are all H2O. The difference is how much energy the molecules have, how tightly they're packed, and how free they are to move. Energy is the key player here. Temperature is a measure of the average kinetic energy of particles, how fast they're moving. Pressure influences how close they're forced to be. Together, these two factors determine the state of matter. Raise the temperature and lower the pressure, and you make it easier for substances to exist as gases. Lower the temperature and raise the pressure, and you push them towards solids or liquids. Water, once again, plays an interesting role. Its phase diagram, kind of map showing how its state changes under different conditions, has some odd features, like the fact that increasing pressure on ice actually causes it to melt, not freeze more tightly. That's why ice skates work. The pressure under the blade lowers the melting point of the ice, creating a thin layer of water that allows you to glide smoothly. It's physics doing you a favour. Understanding the states of matter isn't just about memorising definitions. It's about recognising that matter is always in flux, always responding to its environment. At the particle level, everything is in motion. Even in solids, the particles vibrate. In gases, they zoom. In liquids, they swirl and shift. Matter is never completely still. It's alive with energy, just moving at different speeds. There's something comforting about that. The tea cooling beside you is losing energy, its molecules slowing down, relaxing into stillness. The air in your lungs is expanding and contracting, a gas flowing in and out of your body with every breath. The ice in your drink is melting, changing form but not identity. All around you, matter is shifting quietly, following the timeless rules of thermodynamics, transitioning from one phase to another like scenes in a slow, graceful play. It reminds us that change is constant, but also orderly. Nothing vanishes, it just moves. Solid to liquid, liquid to gas, energy in, energy out. a soft rhythm unfolding endlessly in every corner of the universe. Not every combination in chemistry ends in sparks, explosions, or dramatic transformations. Sometimes things just mix. They swirl together, settle into layers, dissolve, or float. And that's that. No new molecules are formed, no bonds are broken or created, and the atoms remain exactly who they were before they bumped into each other. This quiet kind of chemistry, the realm of mixtures, solutions, and suspensions, is every bit as fascinating as the reactive bond-breaking kind. It's the everyday blending of substances that keep your morning tea warm, your salad dressing separated, and your oceans salty. To understand mixtures, it helps to know what they're not. A mixture is not a chemical reaction. In a reaction, atoms rearrange and form new substances. Bonds break, new bonds form, and the resulting product often behaves very differently from the starting materials. But in a mixture, the components retain their original identities. They're simply sharing space for a while, sometimes very closely, sometimes a little grudgingly. Let's start with the simplest example, a cup of tea. When you steep a tea bag in hot water, you're creating a mixture. Water molecules interact with the compounds in the tea leaves, drawing out colours, flavours, caffeine, and tannins. But chemically, nothing is reacting in the sense of forming brand new molecules. The water doesn't become tea at the molecular level, it just carries dissolved molecules from the leaves. If you were very patient and had the right equipment, you could separate the water, caffeine, pigments, and oils back into their individual parts. That's one hallmark of a mixture. You can separate it by physical means. Mixtures come in many forms, but they generally fall into two categories: homogeneous and heterogeneous. A homogeneous mixture is uniform throughout. You can't see the different components with the naked eye. Salt water is a great example. When salt dissolves in water, the sodium and chloride ions disperse evenly among the water molecules, creating a clear, stable solution. It looks like pure water, but it's a team effort under the surface. In contrast, a heterogeneous mixture is one where the parts remain separate and visibly distinct. Think of a spoonful of granola, or a bowl of vegetable soup, or a vinaigrette dressing where oil floats on top of vinegar. The components in these mixtures are easily identified, and they don't blend uniformly. Stirring may help temporarily, but left to settle, the parts often drift back into their own zones. A solution is a specific type of homogeneous mixture where one substance, the solute, is completely dissolved in another, the solvent. In the saltwater example, salt is the solute, water is the solvent, and the resulting solution is chemically the same throughout. It doesn't matter if you take a sip from the top or the bottom of the glass, the salt concentration is evenly distributed. Solutions can exist in all states of matter. Air is a gaseous solution made of nitrogen, oxygen, carbon dioxide, and other trace gases. Alloys like brass or steel are solid solutions of metals. And of course, most liquid solutions, from sports drinks to seawater, involve water as the solvent. That's why water is often called the universal solvent. Its polarity and small size make it excellent at surrounding and separating charged or polar molecules, helping them mix in smoothly. But not everything dissolves. Oil and water, for instance, famously resist blending. That's because oil is nonpolar and water is polar. Water molecules cling to each other through hydrogen bonding and simply won't make room for the nonpolar oil molecules. The result is a heterogeneous mixture where the oil floats in droplets or forms a distinct layer. That's a suspension, another common type of mixture. In a suspension, particles are mixed into a fluid but not fully dissolved. These particles are usually large enough to scatter light and eventually settle out if left alone. Muddy water, flour in water, orange juice with pulp, all suspensions. They're cloudy, often chunky, and clearly composed of more than one phase. Unlike solutions, which are stable over time, suspensions need stirring to keep them uniform. Somewhere between solutions and suspensions lie colloids. mixtures where tiny particles are evenly distributed but not dissolved. The particles are small enough that they don't settle out, but large enough to scatter light, a phenomenon called the Tyndall effect. Milk, mayonnaise and fog are all colloids. They look homogeneous to the eye, but behave differently from true solutions under the microscope. Understanding the differences between solutions, suspensions and colloids is more than just academic. It affects how we cook, clean, manufacture and medicate. Think of your favourite salad dressing. It's a classic example of an emulsion, a type of colloid where oil droplets are dispersed in vinegar or lemon juice. Left undisturbed, the oil and vinegar separate because they're immiscible. But shake it up with mustard or egg yolk, and those emulsifiers help stabilise the droplets, keeping the mixture creamy and unified. In the kitchen, physical changes like mixing, grinding, melting or freezing are part of the daily chemistry of food. They don't alter the molecules themselves, they just change their arrangement. Shredding cheese, boiling pasta or whipping cream are all physical processes. The chemical structure stays the same, it's the physical form that changes. Compare that to a chemical change, like baking a cake. When you mix flour, sugar, eggs and baking powder and heat them, you're initiating chemical reactions. New compounds form. Gas bubbles of carbon dioxide are released. Proteins denature and recombine. Sugars caramelize. The result is something entirely new, with properties that can't be reversed by just cooling it down or stirring it backward. That's the key difference. Chemical changes are usually irreversible, while physical changes can often be undone. In mixtures, because the individual substances retain their properties, you can often separate them using simple physical methods. Filtration, evaporation, distillation, decanting, all techniques for teasing apart the components of a mixture. Salt can be reclaimed from salt water by evaporation. Sand can be separated from water by filtration. Even crude oil is separated into gasoline, diesel and other products through fractional distillation, a process that sorts substances based on their boiling points. In fact, the principle of separation based on physical properties underpins much of modern chemistry and industry. The ability to isolate and purify substances is what allows us to create medicines, fuels, and materials with precision and control. Even in nature, mixtures play essential roles. Blood is a complex suspension of cells, proteins, and nutrients in plasma. Soil is a heterogeneous mixture of minerals, organic matter, water, and air. Seawater is a solution filled with salts, gases, and microscopic life. Clouds are colloids of water droplets in air. The diversity of life relies not just on chemical reactions, but on how substances come together, interact, and sometimes stay just separate enough. And this brings us back to one of the most calming realizations in chemistry. Not everything needs to react. Sometimes things just coexist. Molecules float alongside each other, mingle, and remain themselves. They can mix and match without permanently changing, like friends at a party enjoying the same space but dancing to different rhythms. Mixtures are about balance, between blending and staying distinct, between structure and motion, between change and stability. They remind us that chemistry isn't always about big transformations. Sometimes it's about presence and proximity, the quiet chemistry of togetherness. Whether you're watching salt dissolve in water, shaking a bottle of dressing, or sipping a perfectly brewed cup of tea, you're witnessing the subtle, graceful side of chemistry, where particles meet, mingle, and drift apart without fanfare. It's chemistry with a light touch, no explosions required, just the gentle beauty of things coming together, staying themselves and making something useful, or tasty, or simply soothing along the way. Some chemical reactions happen so fast you barely notice them. A match flares to life, fireworks erupt into colour, or lightning turns nitrogen and oxygen into new compounds in a microsecond. Others unfold with the patience of a mountain. Iron rusting over years or fossils forming over millennia. And then there are reactions that never seem to happen at all. no matter how long you wait. But whether it's a rapid blaze, a slow decay, or absolute stillness, every chemical reaction has a pace, and that pace is called the reaction rate. The reaction rate tells us how quickly reactants are converted into products. It can be measured by how fast something disappears, like a reactant being used up, or how quickly something new appears, like bubbles of gas or a changing colour. But more importantly, reaction rates tell us that chemistry isn't just about what can happen. It's about how willing the molecules are to make it happen, and under what conditions. Let's say you leave a jug of milk out on the counter. On a chilly winter day, it might be perfectly fine hours later. But on a sweltering summer afternoon, it turns sour fast. The molecules inside haven't changed their personalities. Lactose is still lactose and proteins are still proteins. But the rate at which bacteria break those molecules down has increased dramatically. That's because temperature is one of the biggest influences of reaction speed. In most cases, increasing the temperature speeds up a reaction. Heat is energy, and when you raise the temperature, you give molecules more of it. They move faster, collide more often, and hit with greater force. Imagine molecules as dancers on a floor. At low temperatures, they're swaying gently, bumping into each other occasionally. At high temperatures, they're breakdancing in every direction. More collisions mean more chances for bonds to break and new ones to form. And that's what a chemical reaction is. But it's not just about bumping into each other. For a reaction to happen, the molecules have to collide with enough energy and in the right orientation. Think of it like trying to high-five someone. You can't just brush past them. You need the right angle and timing. By heating up the system, you increase the number of collisions that have the correct amount of energy to push the molecules over the activation barrier. That energy hill they have to climb before a reaction can proceed. Concentration is another big player in the speed game. The more reactant particles you have in a given space, the more frequently they'll collide. It's simple math. A crowded subway station leads to more accidental shoulder bumps than an empty one. Similarly, a beaker full of concentrated acid will react more quickly than a diluted one, simply because there are more reactive particles buzzing around. This is why reactions in high concentrations tend to be faster, not because the chemicals are suddenly more potent, but because they're bumping into each other more often. It's like increasing the chances of finding your lost keys by opening more drawers at once. More opportunities, faster results. Surface area also plays a sneaky but powerful role. If a reaction takes place at the surface of a substance, like a solid reacting with a liquid or gas, then increasing that surface area speeds things up. A single sugar cube dissolves slowly in tea, but crush it into powder and it disappears almost instantly. The same applies to many reactions. More exposed surface means more contact between reactants, and more contact means more chances for chemistry to occur. This is one reason why powdered substances, whether they're spices in a curry or explosives in a firecracker, behave more energetically than their chunky counterparts. The particles at the surface are the ones doing the reacting, and if you increase that surface by grinding or breaking things down, the reaction goes from mellow to dramatic. But not all reactions respond to these nudges in the same way. Some are naturally slow because the bonds involved are very stable and hard to break. Others are slow because they involve multiple steps or complicated rearrangements. In these cases, temperature, concentration and surface area help, but sometimes they're not enough. That's where catalysts step in. Catalysts, those helpful backstage workers of chemistry, don't change the starting materials or the final products. Instead, they offer an alternate pathway for the reaction, a kind of shortcut that requires less energy. Think of it like taking the escalator instead of climbing the stairs. You reach the same destination but with less effort. Enzymes, the biological version of catalysts, are especially good at this. In your body, reactions that would take days or years in a test tube happen in seconds, thanks to enzymes nudging molecules into place and stabilizing tricky transition states. From digesting food to copying DNA, enzymes ensure the chemistry of life runs not just smoothly, but on time. Reaction rates can also be influenced by light. In some cases, photons, particles of light, provide the energy needed to initiate a reaction. This is how photosynthesis begins, when sunlight strikes chlorophyll and triggers the movement of electrons. It's also how some chemical reactions occur in photography, where exposure to light changes the chemistry of silver compounds on film. In modern chemistry, understanding reaction rates is crucial in designing everything from industrial processes to medications. A reaction that's too slow might make a product impractical or unprofitable. A reaction that's too fast might be dangerous, hard to control, or lead to unwanted byproducts. Chemists spend a great deal of time tweaking conditions, adjusting concentrations, choosing the right solvents, testing different catalysts, to find that sweet spot where the reaction is fast enough to be useful, but controlled enough to be safe. Even in cooking, you're playing with reaction rates. Browning meat involves the Maillard reaction, a complex set of chemical changes between amino acids and sugars that only happen quickly at high temperatures. Let the pan get too hot and you burn the food. Keep it too cool and it stays pale and flavourless. Finding the right temperature is chemistry at work in your frying pan. Refrigeration, on the other hand, is chemistry in slow motion. Lowering the temperature of food slows down the reactions that cause spoilage, both chemical changes like fat oxidation and biological ones like bacterial metabolism. It doesn't stop those processes entirely, but it makes them so slow that the food stays fresh for longer. The same principle applies in preserving medicines, storing tissues for transplant, or slowing the decomposition of fossils over geologic time. Sometimes reactions can be so slow that they seem not to happen at all, at least on human timescales. Glass, for example, is often cited as a very slow-moving liquid, though that's more folklore than fact. But real examples do exist. Diamonds slowly turning into graphite, or the transformation of ancient organic matter into oil and gas, all occur through reactions so sluggish that they might as well be paused. And then there are reactions that are fast but fleeting, like the flash of hydrogen and oxygen combining into water in a rocket engine. They happen in an instant, leaving behind an enormous release of energy and little time to observe the details. These reactions are highly studied in fields like explosives, combustion, and propulsion, where every millisecond matters. Understanding reaction rates means understanding time in the language of chemistry. It means recognizing that every molecule is moving, colliding, deciding whether to stay the same or become something new. The rate at which those choices unfold is influenced by the world around them. Heat, pressure, size, shape, concentration, even a helpful catalyst lending a hand. There's something beautiful about that. Every bubbling pot, every rusted hinge, every ripening peach is a slow ballet of molecules interacting. Some are racing toward change, others are lingering in equilibrium, and many are doing their chemistry at a pace that matches the rhythm of the world around them. It's not about being fast or flashy, it's about timing, and in chemistry, as in life, sometimes the right reaction just needs the right conditions, and a little patience, to unfold exactly as it should. Biochemistry is the soft-spoken cousin of big, flashy chemistry. It doesn't erupt into fireballs or fizz over beakers in dramatic swirls. Instead, it hums gently in the background, quietly managing the reactions that keep you alive every second of the day. It's chemistry in a cardigan. Practical, efficient, endlessly detailed, and essential in the most fundamental way. Without biochemistry, there's no heartbeat, no memory, no breath, no thought. Every blink, every yawn, every dream is powered by the tidy, tireless work of molecules behaving just right. At the heart of biochemistry are a few familiar names: proteins, DNA, and ATP. These molecules are the stars of the molecular drama that plays out inside every living cell, choreographed with exquisite precision. And yet, their power comes not from showmanship, but from consistency. Life doesn't need wild reactions. It needs reliable ones. Start with proteins. These aren't just the stuff of muscle shakes and dietary charts. They're the workhorses of life itself. Proteins are long chains of amino acids folded into fantastically complex shapes. Each fold, twist, and loop is dictated by the sequence of those amino acids, which in turn are dictated by your DNA. The shape of a protein is everything. It's what determines whether it becomes an enzyme, a structural support, a transporter, or a signal messenger. Enzymes, specialized proteins, are nature's catalysts. They speed up reactions that would otherwise crawl along too slowly for life to keep up. Without enzymes, even something as simple as digesting a sandwich would take weeks. One of the most famous enzymes is DNA polymerase, the molecular scribe that copies your DNA every time a cell divides. Another is amylase, found in saliva, which starts breaking down starch before your food even leaves your mouth. These enzymes don't just work hard, they work with uncanny precision, recognizing their specific molecular partners like a key fitting into a lock. And what about DNA itself? Deoxyribonucleic acid is the grand archivist of life, storing the instructions for building everything your body needs to function. It's made of just 4 kinds of bases: adenine, thymine, cytosine, and guanine, arranged in different sequences along a sugar phosphate backbone. Despite its simplicity, DNA's potential is nearly infinite. Every strand is a set of blueprints for building proteins, organizing cells, and running the entire show from behind the scenes. But having a blueprint isn't enough. Cells need energy, and that's where ATP comes in. Adenosine triphosphate is sometimes called the molecular currency of energy, and for good reason. It's a compact, rechargeable unit of power used in nearly every biological process. When a cell needs to move something, build something, or send a signal, it often pays for it by breaking one of the phosphate bonds in an ATP molecule, releasing energy in the process. The result is ADP, adenosine diphosphate, which can be recharged later with a fresh phosphate to make ATP again. It's efficient, tidy, and happening billions of times per second in your body right now. All of these reactions, protein folding, DNA replication, ATP cycling, make up what we call metabolism. And metabolism is often described as a kind of controlled chaos. It's a web of interconnected reactions, all happening simultaneously, each depending on the others, all finely tuned to maintain balance. There's the catabolic side, where complex molecules are broken down to release energy, and there's the anabolic side, where new molecules are built up from smaller pieces. It's destruction and creation happening hand in hand, keeping the system alive and responsive. You can think of metabolism like a city during rush hour. Cars, molecules are zooming around, some headed for factories, enzymes, others stopping at gas stations, ATP, still others turning into buses, buildings, or traffic cones, new compounds. And somehow, through all the motion, nothing crashes, at least not often. The traffic lights, feedback loops, the speed limits, enzyme regulation, and the road signs, signal molecules, keep everything flowing. What keeps this city from spiralling into gridlock or disaster is regulation. Cells don't let reactions just run wild. Many enzymes are only active under certain conditions. Some need a cofactor, a helper molecule like a vitamin or a metal ion, to work properly. Others are inhibited when there's too much product, creating a feedback loop that shuts things down before the system overheats. It's a bit like your heating system knowing to stop once the room reaches a certain temperature, not because it's tired, but because the job is done. Take glycolysis, for example, the 10-step process that breaks down glucose into smaller molecules, releasing energy and producing a bit of ATP along the way. It's part of cellular respiration, the long multi-step process your cells use to extract energy from food. If glucose were broken down all at once, it would release too much energy at once and possibly damage the cell. Instead, glycolysis slices it up gradually, storing the energy in manageable packets. Each step is regulated, monitored, and perfectly timed. The same goes with the citric acid cycle, also called the Krebs cycle, where those smaller molecules from glycolysis are further oxidized, And then there's the electron transport chain, the final stage where the big ATP payoff happens. Here, high-energy electrons are passed from molecule to molecule, like a molecular bucket brigade, slowly releasing energy to pump protons across a membrane and generate ATP through a process called chemiosmosis. It's chemistry performing a quiet miracle. One molecule of glucose, fully broken down, can yield over 30 molecules of ATP. But metabolism isn't just about energy. It also handles the construction of new cells, the repair of damage, the response to hormones, the processing of toxins. It manages everything from hunger and mood to muscle growth and immune defense. And all of this depends on biochemistry, on reactions running smoothly, proteins folding correctly, and energy flowing exactly where it's needed. Sometimes things do go wrong. A single misfolded protein can lead to devastating diseases, like in the case of prions, infectious agents made entirely of misfolded proteins that can cause neurodegenerative disorders. Other times, an enzyme might be missing or malfunctioning, leading to metabolic disorders where certain compounds build up or fail to be broken down. These rare conditions offer a glimpse into just how carefully balanced life's chemistry really is. Even so, life is remarkably good at adapting. Enzymes can evolve, pathways can reroute, and cells can compensate for shortfalls in surprising ways. The resilience of biochemistry is part of what makes life so persistent, thriving in everything from boiling hot springs to Antarctic ice. One of the most astonishing things about biochemistry is how universal it is. The same basic processes occur in every living thing, from bacteria to blue whales. The structure of DNA, the use of ATP, the coding of proteins from genes, it's all shared. Life doesn't reinvent the wheel with each new species. It refines it, tweaks it, builds on top of it. But the foundation is always the same. Biochemistry is the chemistry of life, yes, but it's also the chemistry of stability. While other branches of chemistry might aim for speed, transformation, or destruction, biochemistry is more about sustainability. It's chemistry that loops, that conserves, that adjusts. It's how life takes a pile of atoms and turns it into movement, thought, feeling, and memory, and does so without exploding, which, when you think about it, is kind of incredible. You're made of carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and a handful of trace elements. Those atoms follow the same rules as the ones in rocks or oceans or air, but in you they assemble, react, and recycle in ways that produce not just order, but purpose. And they do it all quietly, molecule by molecule, second after second. You don't feel it, and you don't hear it, but it's there, a molecular symphony playing just beneath your awareness. A whispering choreography of proteins, enzymes, and tiny sparks of ATP, all working together to keep the lights on and the gears turning. Biochemistry may be quiet, but it's the soft hum behind every breath, thought, heartbeat, and smile. And in its own subtle way, it's perhaps the most remarkable chemistry of all. The Earth might seem like a solid, steady kind of place, a big rock floating through space, wrapped in clouds and blanketed in oceans. But beneath the surface and above the clouds, this planet is a restless, dynamic chemical system. It breathes, cycles, and changes constantly. The mountains erode, the seas shift, gases mix and drift, and deep below, molten rock simmers in silence. From the churning core to the icy poles, Earth is always reacting. Not metaphorically, but literally. Chemistry is what keeps it all moving. Geochemistry is the study of the Earth's chemical composition, and how those elements interact over time. It explains why volcanoes erupt, why oceans are salty, and how ancient carbon locked in limestone might end up in the atmosphere, or in your carbonated drink. It's the chemistry of rocks and water and gases, of slow drips and explosive bursts, of minerals forming, breaking down, and reforming again over eons. Start deep underground, where the Earth's interior is a hotbed of elemental drama. The core is mostly iron and nickel under intense pressure and heat. Surrounding it is the mantle, a layer of molten and semi-molten rock that convect slowly, driving plate tectonics. The crust, the thin skin we live on, floats on this restless mantle like cracked bits of ceramic on a pot of stew. And when these plates shift, crack, or dive under one another, chemistry gets loud. Volcanoes are one of the most striking examples of geochemistry on display. Magma, formed when rock melts deep in the earth, contains dissolved gases like water vapour, carbon dioxide, sulfur dioxide, and more. As the magma rises toward the surface, the pressure drops, and those gases start to bubble out. It's like opening a shaken soda can, only much hotter and more dangerous. The expanding gases can drive explosive eruptions, hurling ash, rock, and lava into the air. But volcanic eruptions aren't just spectacular. They play a vital role in cycling elements through the Earth's systems. Gases released by volcanoes contribute to the atmosphere. Minerals in the lava slowly break down and enrich the soil. Even the ash, once it settles, can fertilize distant lands or alter climate by reflecting sunlight back into space. Once those volcanic rocks reach the surface and begin to cool, they start a new chapter in their chemical life: weathering. Weathering is the gradual breakdown of rocks into smaller pieces, driven by wind, water, temperature changes, and chemical reactions. There are two types, mechanical and chemical, and it's the chemical version that rewrites the molecular story. Chemical weathering occurs when water, oxygen, carbon dioxide, or acids interact with minerals in rock. Take feldspar, a common mineral in granite. When it reacts with slightly acidic rainwater, it breaks down into clay minerals and releases dissolved ions like calcium and potassium into the environment. These ions might later be carried to the ocean, where they contribute to the salinity of seawater or become part of marine organisms' shells. Rainwater, by the way, is naturally slightly acidic. As it falls through the atmosphere, it absorbs carbon dioxide, forming a weak carbonic acid. This gentle acid plays a huge role in shaping landscapes. Over time, it can dissolve entire limestone formations, carving out caves, sinkholes, and underground rivers. This isn't dramatic chemistry, it's chemistry with patience. One drop at a time, it transforms mountains into sediment. The ions released by weathering don't just float off aimlessly. Many of them make their way into the oceans, where they help regulate the chemistry of seawater and support marine life. Calcium and carbonate ions, for instance, combine to form calcium carbonate, the material used by corals and shellfish to build their exoskeletons. When these organisms die, their shells sink and accumulate on the ocean floor, eventually forming limestone. It's a slow geological bank account storing carbon for future ages. Which brings us to the carbon cycle, one of the most important chemical cycles on the planet. Carbon moves between the atmosphere, oceans, rocks, soil, and living things in a complex interconnected loop. It exists as carbon dioxide in the air, as carbonate in water, as organic molecules in living tissue, and as fossil fuels deep underground. And in each place, it's constantly being transformed. Photosynthesis pulls carbon dioxide out of the air and locks it into sugars in plants. Animals eat those plants, metabolize the carbon for energy, and exhale it again as carbon dioxide. When organisms die, decomposers break them down, releasing carbon back into the soil or air. Some of that carbon may become buried and compressed over millions of years, eventually forming coal, oil, or natural gas. Burning fossil fuels returns that buried carbon to the atmosphere as carbon dioxide. So does cutting down forests, which removes the trees that would otherwise be absorbing CO2. Volcanic eruptions release carbon from the mantle. Weathering of rocks can trap atmospheric carbon in mineral form. The ocean absorbs carbon from the air and stores it in surface waters, deep currents, and marine sediments. It's a grand cycle. Not a perfect loop, but a system with inputs and outputs, feedbacks and delays and a very real influence on climate. Speaking of climate, atmospheric chemistry is where Earth's delicate balancing act really shows itself. The atmosphere is not just air, it's a reactive soup of gases constantly undergoing chemical transformations. Oxygen, nitrogen, carbon dioxide, water vapour, methane, ozone. All these molecules interact in ways that affect weather, climate, and life itself. Take ozone, for example. In the upper atmosphere, ozone forms a protective shield that blocks harmful ultraviolet radiation from the sun. Without it, life on Earth's surface would be exposed to intense UV rays that could damage DNA and harm living cells. But lower in the atmosphere, ozone is a pollutant, formed when sunlight reacts with emissions from vehicles and industry. This ground-level ozone contributes to smog and respiratory problems. Methane, another atmospheric player, is a potent greenhouse gas, more effective at trapping heat than carbon dioxide, molecule for molecule. It's released by wetlands, termites, cows, and fossil fuel extraction. While it's less abundant than CO2, its powerful warming potential means it plays an outsized role in climate change. And like many atmospheric gases, methane doesn't just sit there. It reacts with other molecules, breaks down over time, and contributes to the ever-changing chemistry of the air we breathe. Then there's water vapour, the most abundant greenhouse gas. Is also a key part of the water cycle, moving through evaporation, condensation, and precipitation. Clouds form from water vapour and influence climate by reflecting sunlight and trapping heat. But clouds also serve as tiny chemical reactors, where pollutants, acids, and salts can interact in micro droplets suspended in air. Even rain itself is chemistry in action, distilled water falling from the sky, flavoured with whatever it picked up on the way down. Through all of this, the Earth behaves less like a static ball of rock, and more like a living system. Some scientists refer to the Earth as a geochemical engine, with feedback loops, equilibrium points, and self-regulating processes. It's not conscious, of course, but the interactions are complex enough to resemble something alive. The composition of the atmosphere affects the temperature, which affects the rate of weathering, which affects carbon levels, which then loop back to influence the atmosphere again. It's chemistry with memory, cause, and consequence. The Gaia hypothesis, first proposed in the 1970s, suggested that life on Earth helps regulate the planet's environment to maintain conditions suitable for life. While not universally accepted in its original form, the idea helped inspire research into how biological and geological processes interact. And there's no question they do. The Earth doesn't just host life, it works with it. From the soil bacteria that fix nitrogen, to the forests that exhale oxygen, to the oceans that buffer heat and carbon. Life and Earth shape each other constantly. All of this points to something rather beautiful. We're not separate from the planet's chemistry. We're part of it. Our breath, our food, our bones, and blood. All made of atoms borrowed from Earth's cycles. The calcium in your teeth was once part of a star, filtered through rocks, plants, and perhaps the bones of ancient creatures. The nitrogen in your DNA may have once been lightning in a prehistoric sky, and the carbon in your breath will one day be food for a tree. So when you step outside and feel the breeze, or watch clouds drift, or see a mountain crumble into river sand, know that you're witnessing chemistry in its slow, magnificent stride. The Earth is not just a place we live. It's a vast, breathing laboratory of elements in motion, quiet, ancient, and always changing. Chemistry isn't just something that happens in test tubes, kitchens, and planetary atmospheres. It also unfolds in the great open silence of space, between the stars, inside them, and in the long, cold stretches where barely anything seems to move. Out there, where gravity reigns and light takes years to travel, chemistry is hard at work shaping galaxies, planets, and even the atoms in your body. It's a slower, more cosmic kind of chemistry, but at its core it follows the same rules. Particles moving, colliding, fusing, and transforming an elegant, explosive harmony. Let's start at the most dazzling laboratory of all: stars. These enormous balls of plasma are powered by nuclear fusion, where lighter elements like hydrogen are crushed together under intense pressure and temperature to form heavier ones like helium. This process releases immense energy, which radiates outward as heat and light. But fusion isn't just an energy source, it's also a form of elemental alchemy. Inside the cores of stars, atoms are being reshaped. In the smallest stars, hydrogen fuses into helium, and that's where the cycle ends. But in more massive stars, the fusion process continues. Helium fuses into carbon, carbon fuses into oxygen, then neon, magnesium, and silicon. The process builds up a layered structure inside the star like a cosmic onion, with each layer fusing heavier and heavier elements. This continues until iron is formed, and then everything changes. Iron is the turning point because fusing it doesn't release energy. It consumes it. At that moment, the star can no longer support its own weight. Gravity wins, and the star collapses. In the most massive stars, this collapse triggers a supernova, one of the most powerful explosions in the universe. For a brief moment, a single star can outshine an entire galaxy. And in the heart of that explosion, elements heavier than iron are forged: gold, uranium, platinum, and more. All of it hurled into space at incredible speeds, seeding the universe with the raw materials for planets, moons, and eventually life. It's not just poetic to say we're made of stardust, it's a chemical fact. The carbon in your muscles, the oxygen in your lungs, the calcium in your bones, none of these elements were made on Earth. They were born in stars that lived and died long before the solar system formed. Every breath you take contains atoms that have journeyed across billions of years and uncountable light years to be part of you, here and now. Between the stars, there's more than just empty space. Interstellar space is filled with vast clouds of gas and dust, not dense by earthly standards, but massive in volume. These clouds, called nebulae, are where stars are born. Within them, atoms and molecules drift, collide, and occasionally stick together. Under the right conditions, gravity pulls regions of the cloud inward, forming protostars, the seeds of new suns. As they collapse, temperatures rise, fusion ignites, and a new star is born, surrounded by a spinning disk of gas and dust that may one day become a planetary system. Inside these interstellar clouds, chemistry unfolds in its own slow, frigid way. Temperatures can hover just above absolute zero, and the pressure is incredibly low. Yet even here, molecules form. Hydrogen is the most abundant element, and it often binds into molecular hydrogen, H2. There are also more complex species: water, ammonia, methane, carbon monoxide, and even simple organic molecules like formaldehyde and acetylene. These form on the surfaces of tiny dust grains, acting like miniature beakers in the vacuum of space. What's astonishing is just how complex interstellar chemistry can be. Astronomers using radio telescopes have detected over 200 different molecules in space, including some that are prebiotic, meaning they contain the building blocks of life. Amino acids, alcohols, and even sugar-like molecules have been found drifting in distant clouds, suggesting that the raw ingredients for biology might be widespread in the galaxy. These molecules survive for millions of years, occasionally caught up in collapsing clouds that may form new solar systems, carrying the seeds of complexity with them. As stars age and shed their outer layers, they release heavy elements into space, enriching the interstellar medium. This recycling of matter, from stars to clouds and back again, is how the universe grows chemically diverse. In the early universe, shortly after the Big Bang, there were only a few elements: hydrogen, helium, and a trace of lithium. Everything else was built in stars scattered by supernovae and gathered again into new forms. Closer to home, planetary atmospheres showcase another kind of cosmic chemistry, one shaped by sunlight, magnetism, and life. Earth's atmosphere is unique in the solar system, thanks to its oxygen-rich composition and active carbon cycle. But every planet has its own chemical story. Venus, for example, has a thick atmosphere dominated by carbon dioxide, with clouds of sulfuric acid. Surface temperatures are high enough to melt lead, due in part to an intense greenhouse effect. Mars also has a CO2 atmosphere, but it's thin and cold, with occasional dust storms and traces of methane that continue to intrigue scientists. Could it be geological? Biological? We're still finding out. The gas giants, Jupiter, Saturn, Uranus and Neptune, are chemical playgrounds in their own right. Their atmospheres are mostly hydrogen and helium, but they're also filled with swirling clouds of ammonia, methane and water. Lightning crackles through their skies, sparking high-energy reactions. On Saturn's moon, Titan, the atmosphere is rich in nitrogen and methane, and lakes of liquid hydrocarbons dot the surface. It's cold and alien, but chemically rich, and possibly a place where new kinds of chemistry are still unfolding. Even comets, those icy wanderers of the solar system, are more than just dirty snowballs. When they approach the sun, their surfaces vaporize, releasing water, carbon dioxide, ammonia, and organic compounds. These tales of gas and dust give scientists a peek into the solar system's early chemistry, preserved like frozen time capsules from billions of years ago. In the realm of exoplanets, planets orbiting other stars, chemistry is becoming a key tool for discovery. By analysing the light that passes through a planet's atmosphere during a transit, astronomers can identify chemical fingerprints, absorption lines that reveal the presence of water vapour, carbon dioxide, or even oxygen. As our instruments become more sensitive, we may one day detect the chemical signatures of life on distant worlds, not by seeing the creatures, but by spotting the gases they breathe out and the molecules they leave behind. All of this reminds us that chemistry is not confined to labs or life, or even Earth. It's the language of the universe. Atoms come together, break apart, and reassemble across billions of years and billions of miles. Gravity gathers them, fusion transforms them, cold clouds preserve them, and occasionally, somewhere in all that vastness, they become conscious, able to look back at the stars and wonder where they came from. You're not separate from that story, you're a chapter in it. The iron in your blood, the calcium in your bones, the oxygen in your breath, all of it forged in stars, passed through space, and woven into a living being. The chemistry that built you also built galaxies, nebulae, and moons. You're a collection of atoms that learn to think, to feel, and to marvel at its own origin. In the end, the cosmos isn't just out there, it's in here too. Every time you lift your eyes to the night sky, you're seeing a reflection of yourself, scattered across the stars. And whether it's hydrogen fusing in a distant sun or a molecule forming on a dust grain in a cold nebula, it's all chemistry. Quiet, elegant, and universal. Even in the quietest moments, chemistry is never truly still. A cold cup of tea, a breath drawn in the dark, the gentle creak of wood in a settling room. Beneath it all, atoms are in motion. Molecules shift, electrons dance, and forces balance. It's a rhythm far too small for us to see, and far too constant for us to hear, but it's there all the same. Every moment, every object, every bit of you, held together and changed by the slow, steady, sometimes spectacular poetry of chemistry. Over these many chapters, we've wandered through the vast and varied world of matter, from the tiniest atom to the fire in stars, from rust on a garden gate to the reactions inside your cells. We've seen chemistry move fast, explode and glow, but we've also explored the calm chemistry, the kind that unfolds with patience, weathering stone, dissolving sugar, or folding proteins with exquisite precision. We began with atoms, the smallest building blocks of everything, and yet full of character. With their proton-packed centres and twitchy electron clouds, they're never truly at rest. We followed electrons in their unpredictable ways, discovering how they drift, leap, and arrange themselves into orbitals that define all reactivity. We saw how bonds form, sometimes with cooperation, sometimes with outright theft, giving rise to the endless diversity of chemical structures. We explored how energy drives reactions, how heat and pressure can nudge molecules to collide with the right amount of force, and how sometimes a gentle push from a catalyst is all that's needed. We met acids and bases, opposites in charge and personality, and discovered how even a simple change in pH can tip the scales of reactivity. We moved through temperature and pressure, watching how they shape the way particles interact, speed up, or hold back. We dove into equilibrium, where chemistry reaches a kind of balanced stillness, not a stop, but a hum of matched processes happening both forward and back. Even explosions had their place, as fast reactions unspooled all their energy in brilliant fleeting moments. We traced the drama of carbon and the elegance of organic chemistry, revealing how a single element became the scaffolding for all living things. We followed electrons in redox reactions, always being passed, swapped, or borrowed, and watched how batteries, metabolism, and rust all shared the same basic principles. We met catalysts, the backstage crew of chemistry, and saw how they gently guide reactions without demanding anything in return. We unpacked the secrets of water, that most peculiar and life-enabling substance, whose hydrogen bonds and polarity make it the universal host of molecular life. Then we shifted through states of matter, solids holding steady, liquids flowing, gases flying, plasmas glowing, each one revealing a different kind of motion and freedom. We sifted through mixtures, solutions, and suspensions, learning that not everything reacts. Sometimes things just blend, swirl, or float apart. And in our look at reaction rates, we saw how time, heat, concentration, and shape all contribute to how fast or slow chemistry unfolds. From there, we stepped into the body, into biochemistry, life's own quiet chemistry, and saw how proteins, enzymes, DNA, and ATP form the machinery of existence. Every heartbeat, every thought, every blink is powered by molecules that operate in stillness and speed, with a calm confidence that belies their complexity. And we stepped beyond ourselves, into earth chemistry and the chemistry of the cosmos. Volcanoes, carbon cycles, planetary atmospheres, stardust, and interstellar clouds, all obeying the same basic rules, all driven by the same forces of attraction, repulsion, energy, and transformation. Whether it's lightning in the sky or amino acids on a distant moon, chemistry connects everything. What all of this reminds us is that matter is never dull. It may appear motionless, may sit in your palm like it's doing nothing at all, but even then, it's reacting, changing, or preparing to do so. Particles are moving, bonds are vibrating, electrons are shifting. Even in a moment of silence, the universe is humming with invisible action. Stillness, it turns out, is full of life. There's something profoundly comforting in that thought. We live in a world that often values speed and spectacle, but chemistry tells us that slow, quiet change is just as powerful, and often more lasting. Rocks weather, trees grow, cells divide, oceans absorb carbon, reactions can burn like fire or unfold over centuries. Some need energy, some release it, and some just hover at the edge of balance. And behind every one of those reactions, no matter how fast, how small, or how seemingly ordinary, is a story. A tiny narrative about atoms wanting to be stable, molecules seeking lower energy, and systems finding their way to equilibrium. It's a chemistry not just of things, but of desires, of tendencies, of probabilities. The periodic table isn't just a list, it's a cast of characters, each element with its own quirks, preferences, and style of bonding. Whether we're thinking about the way soap lifts grease, how batteries power flashlights, or how stars turn hydrogen into gold, we're witnessing chemistry in action. It's not separate from us. It is us. The chemistry of water is the chemistry of your blood. The chemistry of carbon is the chemistry of your thoughts. The chemistry of light is the chemistry of sight. So as we come to the end of this journey through the chemistry of nearly everything, I hope you felt the wonder that lies beneath the surface of the everyday. I hope this has been interesting, but not so interesting that it kept you from resting. And if it did keep you awake, well, at least you've learned something new about the world, and maybe about yourself. Before you drift off, or if you're still peacefully listening with your eyes closed, I'd love to know, where in the world are you tuning in from? What time is it where you are? Are you curled up in bed under soft blankets or on the couch with a pet? Are you hearing the hush of night outside your window or the quiet hum of a distant city? Let me know in the comments. I love hearing where this chemistry journey has taken you. And if you enjoyed this exploration, if you found it relaxing, interesting, or gently thought-provoking, please consider giving this video a like or subscribing to the channel. It helps me bring more of this content to you, and it lets me know that these gentle dives into science are bringing a little more wonder into the world. Thank you so much for being here, and for joining me in this quiet celebration of how the universe works. One invisible reaction at a time. And remember, even when nothing seems to be happening, chemistry is always happening. The atoms are still dancing, the molecules are still mingling, and the world, even in perfect stillness, is still beautifully, endlessly alive.